Hi everyone, welcome to this new training campaign which will be about 4G and 5G services. We'll go through end-to-end for the VoLTE voice and RNDB's fallback, which will try to cover as much as details as we can, such as, for example, the end-to-end call flow, signaling features, and also all potential problems, and also the main features which can improve the performance in general for all these kind of voice services. So actually in today's video, we will explore and go through the end-to-end VoLTE architectures, including IMS core and RAN, and also other main topics which will be covered in the next slide. So moving forward, this will be the today contents. Actually, we'll try to cover the end-to-end VoLTE in around 3 or 4 videos. The first video, which is today, will be covering the first 3 points, which is a VoLTE overview, then registration capabilities, and the end-to-end high-level view of IMS. As you can see, the VoLTE overview will be covering these 3 points, which is overview in general about the VoLTE, what is meaning by VoLTE, why we need VoLTE, and so on. Then the call procedures as high level. Then we'll be speaking about the codec scheme, traffic models, and so on. Then the registration capabilities. We'll just check how to check, for example, the network capability, the UE capability, how the UE is requesting to get the IMS, and so on. And also we'll go through the how the network in general indicates voice over PS capabilities to the UE. And then the first part also will be covering the architecture in general for VoLTE, including the IMS, and we'll give a high-level introduction about it as a theoretical point of view. Then we'll end by this end-to-end high-level view of IMS code, and this is very important because whatever we explain during the IMS or the VoLTE architecture in general, it will be like here, it will be like a practical experience, which is try to simulate whatever theoretical we have explained here. So it will make it very clear for you about the IMS entities and what kind of functions is being implemented in each of those functions. Then the next session will go through the end-to-end call, which actually will be more easy after you understand the first 3 parts. So now let's move to the next slide. Okay, actually, this is just an introduction for VoLTE in general, what it means by VoLTE. As you know, that the VoLTE, as mentioned here, stands for Voice over Long-Term Evolution, right? And this is like a technology which is being introduced to use the voice over the BS network or the BS network, and previously in the traditional network we used to have 2G and 3G, which was operating over the CS network. And as you know, that currently the VoLTE is the mainstream for the 4G network, and now it's very, very important to optimize and to make sure that network is very optimized for the 4G if you are going to introduce, for example, 5G standalone, because as you know, 5G standalone is not supporting fallback to 3G. So the VoLTE network will be the backbone for the 5G standalone network. Same concept as whenever you used to have VoLTE, we used to have this SRVC, which is being falling back to CS network during the call to ensure the call continuity. This is the main idea. And as you know, that the VoLTE or the VoLTE, like for example, is operating over the BS network. So sometimes you need to communicate with the CS network. That's why VoLTE in general relies on the IMS. That's why we have this kind of the IP multimedia system, which will be explaining this session in details as much as we can for all the entities and function and so on. So VoLTE in general operate or relies on the IMS in order to operate. And in general, the IMS, as you know, it's facilitate the communication between the BS and CS network. So it's make the translation and it can communicate between the CS and BS network. Now, I would like to take you through very important concepts which you will usually hear about it, or whenever you are working in VoLTE networks, you'll see this kind of concepts. For example, we have something called transport protocol, which is TCP and UDP. For example, as you know that we have in the VoLTE, we have this IMS protocol, which is called SEP and SDB. We'll explain both of them, which is session initiation protocol or session description protocol. We'll explain both of them. And we have this one for mainly for the signaling, for transferring the signaling messages through the CI5. And this is using, for example, the transport part because it's using this acknowledgement node. We'll explain this in more detail, but just keep in mind this kind of expressions which you have it. And then we have this RTB and the RTCP. We also explain the differences in the upcoming sessions. And we have different codecs in VoLTE, which is including AVS, MR, wideband, and MR narrowband. And we'll show also all of them in the next sessions. Then we'll have, as you know, in VoLTE we have two bearers, which is default and dedicated bearer. This also will be covered. And as we just mentioned, that whatever the CEF, for example, is operating over the TCP because it's having acknowledged mode, while the RTB and the RTCP operating over the UDP because it's have unacknowledged mode. It doesn't require any acknowledgement. We try to explain this part as well. Then we'll go through and also the IMS entities in details as much as we can. So you can explain what is means by SPC, what is the CSCF, and what is the MTAS or MMTEL application servers. And we'll go through the registration process. We have, for example, two registration process. We'll explain in them. Then we'll just explain about some interfaces. So just this is a quick interview. Now let's move to the next part. Okay, this slide will be explaining about the traffic model scheme and scheme in general and speech codecs for the VoLTE. First of all, I would like you to know that VoLTE is unlike the data. Data, for example, is transmitted every 1 millisecond, while the speech or the VoLTE packets is transmitting, as you can see here, every 20 milliseconds. This is the first point I would like you to know about it, which is very important as well for your knowledge. And actually, there are two states of voice in general, voice services. There is something called talk spurt and silent period. And actually, the main difference in that part, that this talk spurt, this means that it's already ongoing voice frames in uplink and downlink, and it will be transmitted every 20 milliseconds, which means there is ongoing packets generated during that time. While this silent period, actually, this is being used in general to try to save the UE power or UE battery. And this is the UE, for example, transmit something called SID, which is we stands for silence insertion descriptor. For example, this is used by a DTX mechanism, which uses this silence descriptor frame to actually minimize the power consumption by the UE when there is a period of like inactivity, user inactivity. For example, one of the users is not speaking, so he will start sending that part. And this kind of SID is being sent every 160 milliseconds, as you can see here, for this the interval between them, and it's having a particular size. For example, if you are speaking IB version 4, it will be 56 bits, as mentioned here. And sorry, if you are speaking about the MR, it will be 56 bits. And if you are speaking about EVS, it will be around 64 bits. And so it's having a known transmission period and also packet size. And actually, here is where the inode B can distinguish between the actual silent call or between this kind of SID. It's through two different things, right? The first one, intervals, because it's having 160 millisecond intervals. So the inode B will understand that this is not a silent, it just the user is not transmitting, there is in DTX state. Because of this, there is no data, for example, being transmitted this particular thing, or through the size of the bits, as having fixed size as well. So the inode B will understand that this is not a packet, which is packet will have a different size actually also compared to the which is depend or rely on the actually used coding scheme, which we are going to speak about. Actually, in coding scheme, as showing here in this particular part, we have three different types of coding schemes, which is initially it was AMR narrowband and AMR wideband. And AMR narrowband, for example, and wideband, was initially being used. And this is the bit rates which can be used for them. For example, the narrowband starting from 4.75 till 12.2. Then the wideband as well, we have it from 6.26 till 23.85. Then in 2014, this EVS, which has been introduced. And in general, EVS allows for high definition HD VoLTE speech coding and provides more significant gains, as mentioned here. So now, actually, this expected that the EVS will be the mainstream now in the 5G network. And within this, in EVS, it's supporting narrowband, wideband, and something called super wideband. So this is the main idea about the codecs. Just some important notes about the codecs in general. Actually, first of all, the higher the rate, for example, assume the user is using now MR wideband 23.85. So the higher rate actually can have some impact on the capacity in general, especially the PDSH. For example, the higher rates means the higher the packet size. So this can impact, assume that you have many users on the site, all of them using 23.85. So this can kind of increase the capacity, but in terms of PDSH consumption or BRBs. And actually, the higher the codec rate, this is supposed to be that you will have a better quality. And one of the important points also we are going to discuss, the codec rate in general is usually discussed or negotiated between the MO and MT users, the originally and intermediate users, and at the call setup. and usually it remain all the time without any change unless there is one new feature being introduced. We'll try to explain in the feature part in details. So now let's move to the next part. Okay, this part actually will be mainly try to cover the main functions of the IMS and also some of the existing network in the network of the even PCRF and other entities as well. So actually, let's try to go first through the IMS entities, try to explain the theoretical part, and actually in the end of this video also will be explaining high-level code flow of the IMS. This will make it more clear about the functionality. So, for example, if assume the user already initiated a call. So, as you can see, this red line, the red line will be going through the user through the serving gateway, packet gateway. Then it will be transferred to something called P-CSCF, which is actually P stand for proxy, and CSCF standard for call session control function. And actually, the main function of this primary proxy CSCF, the main function that, as you can see, it acts as the first point of contact. Like whenever there is a call, the EBC will start communicating with the PCSCF. So it's the first point of contact, and it's responsible also for forwarding all the SIP messages, which will be later on received or sent by the serving CSCF, and we'll explain about this part as well. So this is a second function, and there is something called also quality of service reservation. If you quality of service reservation, for example, assume that already that dedicated bearer has been established or need to be established, so the PCSCF need to communicate to the PCRF through this RX interface to ask him to start establishing the PC rules or to start the dedicated bearers, which is the KCI1, in order to start making or having the call being generated. So this was the third function. It's called quality of service reservation. Moving forward, actually for the I-CSCF, it's abbreviated for interrogating, and CSCF, as we mentioned, call session control function. And this is actually the most important function about the I-CSCF. It's try to allocate if the user network does not know which CSCF is being registered to this particular user. So the I-CSCF will allocate the registered CSCF in order to try to start forwarding directly from the proxy to the CSCF all the SIP signaling. And how this being done, the I-CSCF usually will go and check with the HSS, which is home subscriber server, to check about the user, for example, database, to find this user's IP and all the information to know, for example, this particular user is being registered to HSCF. Assume that you have 4 SCSCF in network, so it will understand from HSS it's being registered to 1 or 2 SCSCF 1 or 2 or 3. This is what it means by allocate registered SCSCF. Second important point, actually, it's for the incoming calls. Whenever there is incoming calls, for example, I'm the mobile terminating, it will be used as an entry point, which means that it will be as a first point of contact. This will be explained in more details in the IMS call flow. This will be explaining this part in more details, but it will be acting in incoming call as at the first acting point or first point of contact, that whenever there is a call being received, this will be the first entity which should be going to receive the SIP invite message, as an example. And here it's written the function of that, and this is GW referred to gateway, which is just what I have explained now, which is being used as incoming for the incoming calls as the first point of contact. Then moving forward, actually for the SCCF, actually there is different function. The first one is the registration process. For example, if the user is going to register to the IMS, the authentications and this kind of things will be done through the SCF. SCF need to communicate with, for example, the HSS or the UDM and 5G to obtain this kind of something called the authentication vector to challenge the users and start make the users authentic and try to complete the registration for the users to the IMS network in general. So this is the first function. Second function, actually, it's about something called user service handling, as mentioned in the right here. And actually, this means it's processing and responding to all the SIP signaling messages from or to the users. For example, all the SIP signaling message will be processed by the SCF. This is actually the main idea. And yeah, and also to have other functionality. For example, something called forward the SIP request or response messages to the corresponding domain. For example, assume that this that the user's originating call was under the BS network while the terminating is after the CS network. So this means that this call needs to be redirected to the CS domain. So it will, for example, forward all the SIP messages to this entity which is called PGCF, which is responsible for this kind of called CS interworking function to try to find the user who's being located in the CS network. This also will go through the sum of it now. So this was the second function which means user handling, user service handling. And S actually stands for serving. Okay, the serving means that this will be the serving function for the CSCF to the users all the time, which is again responsible for the SIP messages processing and processing and forwarding and so on. So now moving forward for the most important entity within the IMS, which is called MTAS, or sometimes they call it MMTEL, which is actually referred to multimedia telephony application server. That's why they call it TEL, AS. AS referred to application server. And we have different application server within the IMS. One of them is the MTAS. And actually this function it's one of the most important functions which have it in which we have it in general in the IMS, because it's responsible for many things. For example, the first part it's responsible for, it's something called managed service establishment between M1 and MT users. Every time the user is going to make the call, the SCF need to go and check with the MTAS. It needs to check with the MTAS about the user, for example, status. What kind of status he's able to, he have a credit or not, he can make a call or not. What is his current status in network? He having pairing services or not? This is SCF need every time to go and invoke the MTAS, asking about the originating or even terminating calls, that he's able to perform the call or not. So this is the first function. It's called managed service establishment between M1 and MTUs. And then it's managing a lot of supplementary service, as you can see. For example, the first one is called RBT. This is the ring back tone. For example, if you have a ring back tone, will be addressed by the MTAS as well. And then you have this, if you have a call conference, also by the MTAS. Call waiting, pairing service, and so on. This is, and also other things. For example, if there is any restrictions or a specific parameters being applied for this particular user, this will be all handled by the MTAS part, which is very important. Again, it's managing all the supplementary service. And the most common one, actually, I think, which we always know, which is the ring back tune, call conference, and call waiting. This is the most common, which we know. Then this function, this is entity which is called BGCF. Actually, BGCF stands for Breakout Gateway Control Function. And actually, the main responsibility of that part is trying to responsible for selecting, for example, something called MGCF or the MGW. For example, the MGCF, this is mainly responsible for the CS interworking function. Whenever you are trying to reallocate or try to redirect or route the call towards the CS network, this will be provided by the MGCF and the MGW. And what it means by MGCF and MGW, first one, MGCF, this is called Media Gateway Control Function. And this is mainly responsible for providing the control plane and for the control plane for the interworking towards the CS network. This is responsible for the control plane part, which is redirecting the data towards the CS network. And this is means what by the control plane? It means it translates, for example, between the SIP messages and the corresponding messages in the CS domain. As you know that this is IP network and this is CS network. So there should be some entities which is translating the languages between both of them, which is being done by the MGCF. And MGW, actually, this is the same function as the MGCF, but this is for the user plane. This one for the control plane, which is the same messages, while this one for the user plane, which is, for example, for the speech packets, which need also to be transmitted from here and there. So this is actually provide the user plane interworking for the CS network. This is the main idea about that part. So this is actually the main function of these two entities. Actually, the last two entities which I would like to explain, which will not really use it that much, or will not hear about it, especially in the remaining of this session. The first one is about something called MRF, as you can see above here. This MRF actually provides the user announcement to the user. What it means by providing user announcement to the user. For example, if you assume that the user has finished his credit or his balance, then the network will send an order to the MRF, in order to send announcement that the balance has been finished. So the MRF It's actually, if you look into this part in the bottom right here, it's having MRF. It's having control plane and user plane. So the control plane will just forwarding to the user plane, asking him to announce that to this particular user that his balance has been finished. This is the main function of that part, and this is just for informative or theoretical information, because it will not be included in our call flow, for example. Then the last entity, which I would like also to explain it, it's about something called IBSM gateway, which is actually, if you look into this abbreviation for that part, it's called IB short messages gateway. And this is the same function as the CS interworking function, but this is for the SMS part. This is making SMS interworking function, which is provides interworking between the IMS network and the traditional SMS networks. This is actually the main function about it. Then the important part, which should be ending by this slide, which is very, very important, we just would like to speak about this kind of interfaces, which is called RX, GX, and the responsibility of the PCRF, and how in general the IMS communicate to the EBC and the PCRF network in order to ask them to establish, for example, the dedicated bureau, which is the PCI1, right? So actually, what will happen once all the call and all the SIP signaling have been processed? So the last step will be that the proxy CSCF will communicate with the PCRF through the RX, which is asking them that the session and media related information it will be obtained. Session and media related information, which means the XI1, for example, information will be obtained from the PCSCF towards the PCRF via the RX interface, which is asking the PCF is asking the PCRF to start establishing the dedicated bureau. And here is where the communication will be being done. And this is usually happening during the dedicated bureau establishment after all the SIP signaling has been completed. And the main idea is just to establish this kind of QCI1, which is the dedicated bureau, in order to start making the traffic start flowing, which is called RTB, for example. Then the last part here about that part, then the PCRF need to communicate this kind of information to the ABC network. And we have two interfaces, which is called GX and GXX. GX, we can call it in general, we call it usually GX. For example, this is information that the BCC, the PCRF will assign the BCC and quality of service rules, or will provision the BCC and the quality of service rules to the packet gateway via this GX interface, packet gateway and serving gateway through the GX interface. So this is the PCRF will inform the packet gateway and serving gateway to start creating a session for the quality of service 1, for example, or the PCI1 with specific quality of service, in order to after that both of them, or the serving gateway and packet gateway, will start communicating with the MME and tell you reach the users in order to establish the dedicated bureau to this particular user. So this is the main idea or the main concept of that part. So now let's move to the next part. Okay, in this slide, actually discussing about two important concepts as well, which is the first one, what kind of bureaus we have in VoLTE and what kind of protocols, different protocols we have. As you can see in the left side here, we have two different bureaus being supported by the VoLTE. The first one was called default bureau, which is the PCI5. And actually this responsible for all the SIP signaling transferred between the users and the IMS network. It will be all done through the PCI5. And as you can see, it's using the SIP. And this is usually transmitted through the something called transport protocol, which is called TCP, through the IP. And this is used acknowledgement mode, that all the data need to be acknowledged by the users whenever there is a transmission between the user and the unit B. So it will be acknowledged at the RLEC layer. Then the second part is called the dedicated bureau, which is QCI1 for the voice services, and can be, for example, QCI2 for the video services, because IMS is handling both voice and video, but the VoLTE in general using QCI1, and this is mainly responsible for handling or carrying the data or the speech in general, which can be again audio or video. Audio, which is QCI1, video, which is QCI2. So the speech and the audio will be carried through the QCI1, which is through this protocol, which is called RTB, real-time protocol. And this is usually used unacknowledged mode, which is being transferred through this transport protocol, which is called UDP. And here I mentioned something called ROHC. Actually, this is the feature which is called robust header compression. This is only applied on the XI1 through the BTCP layer. This will be applying through to try to reduce the size of the packets and this will be explained in more details in the feature part. Then the second part, it's about the quality of service. As you know that voice in general or VoIP in general require implementation of quality of service, and quality of service means that you need to guarantee a specific, for example, packet delay or packet or error loss rate in order to ensure the performance in general for the VoLTE, because at the end, especially for the PCI one, for example, even for the signaling, but for the voice call, it's very sensitive. For example, the user will feel if any problem, he will feel it directly because this is real-time data. It's not the download, for example, or the base data. So that's why it's required a specific quality of service. There is actually this, I just give the part of the PCI 1, 2, and 5, which is related to our session, especially 1 and 5. But this kind of table, you will find up to PCI 9, for example, and you'll have a different, for example, you find a different packet delay budget. For example, the data can be used up to 300 milliseconds, because again, this is not a real data, so it doesn't require a strict quality of service. So here, for example, the packet delay budget for the quality of service one, which is using something called guaranteed bit rate, and having 100 millisecond packet delay budget. And it's really important to understand that, because, for example, if you are doing any optimization in the network, we need to consider all the time the budget or the packet delay budget which is being allowed for the VoLTE. Assume that, for example, you would like to increase the retransmission or HARC retransmission times. For example, instead of 4, you need to increase it to 8 or 6 or 7 or whatever. So you need to calculate how much it will take, because if you are crossing this value a lot too much, the user will be impacted. So you need to all the time consider this kind of packet delay budget during your optimization process. And as you can see that the PCI 5 is having higher priority compared to PCI 1, because signaling in general is having higher priority, so it will giving high priority during the scheduling process through compared to all the other PCIs, not only PCI 1, but it's having like kind of a higher packet loss, as you can see here. And this is responsible for IMS signaling, and this is for the audio or the conversation in general for the voice. Then moving to the second part, it's about the protocol stack supported by VoLTE in general. What kind of protocol stack we have in VoLTE? Okay, you can see the green part and the yellow part. The green part, it's about the user plane, IMS user plane, and the yellow part is about the IMS control plane. And this is the user side. Here we have the layer 1, and then we have the MAC, then we're going to RLC, BDCP, then we're going to the upper layers, which is IB, UDP, and then we have this kind of called RTB and RTCP and the codec, which means that the codec or the speech in general or the voice call or the data of the voice call is being transmitted using this protocol, which is called RTB and RTCP as well. And this RTB is referred to real-time protocol, or the other one is called real-time control protocol. And actually the differences between both of them, they work both together, but the RTB in general itself is responsible for to carry the data, which can be audio or video, as we mentioned, and the RTCP is responsible for providing feedback and control information about the RTB stream. For example, what it means by that: assume that the RTCP packets in general are sent from the receiver side, the terminating side will be sending the RTCP packets back to the sender, and these packets will contain a lot of information. Like this information can be, for example, the number of packets received and the amount of data received, and also the quality of service of this particular data. So this information can be used by the UE originating. For example, it can be used by him to adjust the transmission rate and the quality of service. For example, in case if some particular cases that the user originating would based on the data received by the RTCP, which is controlled or monitoring the RTB performance, that will decide to change the transmission rate, as an example. So this is overall idea about the user plane. For the control plane, which is mainly about the SIP messages, as we mentioned, it's using TCP, transmit over the TCP, and this is using acknowledgement mode. And this is doesn't have this kind of which is or ROHC, which is robust header compression, as you just mentioned before, and this is from the UE side. And as you know, for the GNOT B side or the ENOT B side in general, it doesn't decode the higher layer information above the BDCP. It doesn't have a visibility over that part. It's just working as a relay or a transparent entity, which is just forwarding all these messages to the other entities until it reaches the IMS. So actually all the data which is here, it will be transferred through the S1 interface S1 interface and interface to the BTS, then the BTS will be transferring all the data through the S1 interface toward the serving gateway and BGW until it reaches to the IMS. This is what we have. This is in general the main description about that part. So just in summary, again, for this part, that the RTB is used to carry this dedicated bearer for media traffic, and the SIP or something called SDP. I didn't explain. I explain it now. We have these two protocols called SIP and SDP, which is session initiation protocol and session description protocol. I will explain it in more details and whenever you go to the call flow to make it more clear for you whenever we discuss about it. So this is overall, and the SIP is responsible for carrying all this IMS signal information through the XI5. So let's move forward. So before moving into the details of the call flow and signal and registration and other stuff, I would like to take you through a very high level of the VoLTE call procedures in general. So actually, you can say it's being divided into 4 steps. The first step, if the user is not being registered at all as a network, so you need to initiate a registration or attach message to get the default peerer, which is QCI 619. This is the first step. Then after he got the QCI 619, the user himself will start initiating a BDN connectivity request to the MME, asking him I would like to establish my IMS ABN and so on. So, and to acquire for example, the addresses or the IP address of the IMS network, which is in general the proxy, specifically about the proxy CSCF, which is the first point of contact. Then after that, the MME will forward this request to the other entities and it will establish this default peer XI5, and it will assign or inform the user about the IMS addresses for the user. It will transfer all this information within this kind of step. Then once the user got the XI5 established in the network, he now will start initiating the IMS registration, because all of this is not he's still not yet registered to the IMS network. But once he have a XI5 being established, you will now being able to send all the SIP messages towards the IMS network. So this is the third step. You will be initiating the IMS registration, and we'll covering all these in details with signal context and the second part of this video. Then after he make the registration now and all the SIP signaling being done, then the users will initiate the VoIP session, and the network in general or network will start initiating and assigning the dedicated bearer or configuring the dedicated bearer for the UE between the UE and the network in general. And here where the media flow will be established between both originating and terminating, and then now the RTB media will start being generated and the speech traffic in general. Then the last part is about releasing the call. Hello everyone, welcome to the second session of VoLTE training campaign. In today's video, we are going to cover 2 points which relate to the registration capabilities for the IMS and the VoLTE in general, and this will be covering the end-to-end call flow for different aspects, including the IMS and even the 4G attach and so on. We'll go through details in next slides. Then we'll be ending by the end-to-end mobile originating call flow from the IMS point of view, and this will simplify the next sessions about the details of the end-to-end call flow, including the signaling points and so on. So let's move forward to see what we have. So before jumping into the details, I would like to recall what we have ended by in the previous session, which is related to the high level of the VoLTE call procedures. As you remember, I mentioned that it's being split into 4 parts. The first part is about the 4G attach. Initially, once the users get connected to the network, you need to attach to the ABC on the 4G network in general. So we'll explaining the end call flow and some of the message contents. And the most important, it's about the capabilities of the voice domain and so on. So if you look into this figure in the top right here, this is just showing high level view of the attached request message, which is including a lot of information, including the attached type, EBS mobile identity. For example, the user need to send his identity either using MZ or GUTI. We explain whenever he can use MZ or GUTI, and he need to send his capability, which is highlighted by red color, to let them know about his own capability. And also you need to give some information about the voice domain preferences for the user himself. This will be explaining in some details, especially the last point here. And here it's about some information about the BDN type. For example, he's supporting which IP version, for version 4 and 6, or both of them and so on. And the second part, it's about the BDN connection. Once the user did the attach to the ABC network, he now need to request for the IMS ABN and also you need to acquire the P-CSCF IP in order to be able to start the registration to the IMS network. So here it's like P-CSCF discovery, as you can see in the bottom right here, and we'll explain the call flow as well and the contents. As you can see here, this is IP address. Then the third point, it's about the IMS registration. Once he got the XCI5, now he opened the channel, he can start communicating with IMS, but he needs to register himself first to the IMS. So he will go through the end-to-end call flow as shown in the writing. Then we'll be ending about the high-level call view, which is very, very interesting part. This is one of the most important. That it will facilitate that make it you understand easily about the call flow in general. So let's move forward for the next part, which is related to the 4G registration or 4G attach. Okay, this is actually here we're going to explain the end-to-end call flow for the attach in the 4G. And actually, the main idea that the users, whenever is going to make attach, the main idea here and the most important information which you need to know about, which related directly to the VoLTE, it's related to the VoLTE preferences and so on, and IMS preferences, which is usually including the attach message. But it's also important to understand the overall call flow. So let's see what we have. Initially, when the user does attach, he will send the attach request as shown here. It will go through the inode B. As you can see, this dotted line. This means it's transparent for the inode B because this is NAS message. So it will go through to the MME. And usually this message will be piggyback in the S1AB initial UE message. So you will find a message called initial UE message sending from the inode B to the MME, and this one including the attach request which is being sent by the user because this is using its NAS message. And this attach request actually including many important information. We'll go through the most important which related to the VoLTE. For example, the UE identity and capabilities, and also the usage settings which related to the voice domain in general. And this is will be our focus point in the next slide, which contain the details about that. Once the attach request is being sent here from the UE to the MME, the MME, after he received the attach request, he need to acquire some information or to collect some information from the HSS about the user identity, for example, his location and so on. So what will happen? The MME send something called ULA, which stands for update location request. This is including actually what kind of RAT, for example, is coming in 4G, and also the MZ or the GUTI information for this particular user, which is being reported and attached. So the MME is requesting to HSS to share this kind of subscription data for this particular user, and also all the related features supported for this user, especially for the HSS features. So the HSS will be replying with the subscription data and the supported feature. So as you can see in the point number 2 here, the once the MME triggered this diameter update location, which is the HSS will now return the MME. It will send the quality of service for this particular users, which is being returned in the HSS, and also the geographic position, which was already shared. And also at the end, it will inform the MME that this user is being allowed to attach to the network or not. There is no restriction, for example, in this particular user. And actually, once and during this message, now the HSS can store updated information about the user location once in this particular ULA. And this is ULR. This is the response for the update location response. So this is very important as well. Actually, in between, there is some authentication security messages should be there as well to make sure the user is authorized to access to the network, and also the authentication process, but I just excluded for simplicity point of view. So once this one is being received now, the MME need to send to the serving gateway something called create session request, as you can see here, create session request, and this actually message should go to the BGW, and this is requiring that the user the MME would like to open a tunnel with the serving gateway and BGW as well. But since there is no direct communication between MME and BGW, it will go through the SGW. So if you look into that part, the create session request, including a lot of information. One of them is the MZ or GUTI, for example, the MME TID for the control plane. Actually, the MME is telling them that my GTP or the tunnel endpoint control plane is it's informing them about its GTP tunnel endpoint. And the tunnel endpoint or GTP in general, it's like the radio bearer between the UE and UE and the E2E, which you use to carry the traffic, for example, or the signaling and so on. So this is like informing them that it would like to open now to have a tunnel between the serving gateway and MME and also the packet gateway. And also it's telling the serving gateway about BGW address IP to to make sure that the serving gateway will forward this kind of message, which is create session request, to the appropriate or the correct BGW. And also about the BDN type, which is being sent in the attached message. BDN type, actually, it's just the user was telling them that I'm supporting, for example, IP version 4 or IP version 6. In case if user supporting both of them and the network supporting IP version 6, so the user will be selecting IP version 6. This is in case of that. And the IBN type, for example, this is initial, it will be, for example, for data or web or whatever, and RAT and quality of service. So the same message will be forwarded from the serving gateway to the BGW with the exact same content. So the next, actually, after that, the BGW will be responding with create session response as showing here for this create, and now it will be do the same information. Now, do you want to have end-to-end to open end-to-end channel in terms of GTP or the tunnel endpoint? So it will tell them my IP is XYZ, and my tunnel endpoint for the user plane and control plane, UB is user plane and CB is control plane, is this. This is my tunnel endpoint. So now this connection or the tunnel end-to-end tunnel endpoint or GTP is being now created between the serving gateway and BGW, and it will tell them what kind of BDN type is being selected. For example, IP version 4 or IP version 6. And it will give them information about the quality of service and the BS peer identity in general. For example, which KCI is going to be used, what kind of information for the quality of service, and so on. So the serving gateway will return the same information to the MME, but it will add some information on top of that. For example, here it will add its own IP addresses for the serving gateway to the MME to make sure the S1 connection is being created, and also it will add the TE tunnel endpoint for the packet gateway as being sent here for user plane control plane, and the remaining information was just being mentioned. Once this message is being received the MME need to communicate back to the E2E through asking the E2E to start creating the context for this particular user. So now it will be sending this initial context setup request, which is actually the equivalent to attach accept message and active default ABS peer request. So in this message, actually, it will include almost the same information which being sent here, except for for sure the TED or this kind of information just between these three entities. But the most important, it will have the ABS peer, quality of service, and also the MBR messages. And this is in the error interface, you'll find this one called attach accept and also activate default EBS peer request. By the way, in the attach request, this is also related to the BDN connection request message. So, and this is both of them is being piggyback in the initial UE message. So once this message is being sent to the UE, now here this will be the bearer will start like creating the bearer for this default bearer between the UE and the E2E. Once it's being successful being done between both of them, the E2E will responding back for this initial context stop request with initial context stop response, which is now it needs to tell them what kind of my information. For example, what kind of my E2E TID as well, just to to open a channel now between the E2E and serving gateway as S1U, right, user plane between the E2E and the serving gateway. So it needs to send, it's also a GTP tunnel endpoint. And it will then tell that your downlink path now can be to open the downlink path from serving gateway to the E2E, and need to tell them about its own IP and tunnel endpoint. So this is the main point here. After this message, actually, the UE will now send directly to the MME through the next message that, okay, attach is being completed, and now the default peer is being activated, and attach being completed now successfully. So the last point now, which is very, very important, as mentioned here, after all that, the MME need to inform the serving gateway about this kind of information, which is the E2E tunnel endpoint and the IP, which actually being completed after the setup. And the main idea to make sure that now the uplink and downlink path is being created between especially the E2E and the serving gateway for the user plane part. So it will, last point here, you can see it will send modified bearer request, which is sending all the information about the BS, which is being already acknowledgement in 8 and 9, and the information about the E2E, which is the tunnel endpoint, and the IP of the UE, the E2E. So now this process is being completed for the registration. Now, next slide, we'll go through the details about the directly related information to the VoLTE call in general. So here I would like to take you for very, very important information. It's related to directives of VoLTE. For example, if you would like to confirm or to check during the troubleshooting or in general what kind of capabilities we have in the network, even from the U side or from the network side. So you need to check the attach request message. This can be checked from drive test and example, or initial UE message from the S1 AB traces in case if you have Wireshark or you have traces being open for both of them. It will both of them almost contain the same information. But the most important information related to the VoLTE, it's actually need to look into two parts. As you can see in the right side here, you have something called voice domain preferences and UE usage settings. You'll find two pieces of information under that part. The first one called UE usage settings, whether it's voice centric, and this is having two types. It's even voice centric or data centric. For example, the user it's himself, even the device or the SIM card is not supporting voice at all. So he will be sending data centric. So in this case, he is not able to perform at all. And the second part, for example, the voice domain preferences for EUTRAN. This one actually having four domain or four types. I will explain the 3GPP definition shortly about that part. But for example, it can be CS only, which means it will be CS fallback. And it can be IMS, as you can see here, IMS PS voice preferred, and CS voice as a secondary. So the preferred one is IMS, then followed by the CS. I will explain what it means by this through some flow now, but this is just keep in your mind that there is four types of the voice domain, but the one which you use usually it's IMS being preferred and CS as a secondary. Then this one is just the UE is telling the network the the core network about its own capability. So it's telling them, yes, I'm supporting this service C2G RAN and UTRAN. The capability is being supported. So it's telling them their capability. Once the MME receive this message, it's need to respond back about the network capability itself as well. So for example, in the second message you can see down here, attach accept message, I'm highlighting the most important information to the VoLTE in general. You can see it's sending something called IMS, voice over BS, is being supported. So now the network, the core network is confirming its own capability that I'm supporting IMS. So in case, for example, you found that here this information being sent as IMS preferred, but the IMS replied was not supported, this means the IMS or the VoLTE call is not being supported, and you need to check with the core team what kind of actions need to be done from the core side. So now let's explain what it means by this in more details, voice-centric and IMS voice preferred. Okay, as you can see in the two figures in the left here, the first one here in the top left is showing that the voice domain preferences can have four types, as I mentioned, this part. It can be even sent as CS only or IMS only or CS preferred and IMS secondary and the IMS preferred and CS secondary. And this is the one usually used for the VoLTE network or the IMS. So the first one, CS only, means CS fallback only. And this one means, for example, CS preferred means that the CS or CS network is CS feedback is more preferred compared to IMS, and this is the opposite way around. So how this works actually, we have this two piece of information, something called US voice centric, and the second one for that part. So I just quoted one example from the 3GPP. As you can see here, the user initially set his preferences as IMS PS voice with CS voice as secondary. So the IMS is being preferred and CS as secondary. So what the network will do? Initially, the user will be sending this message. So the user will initiate this combined ABS MG attach procedures, and if the attach is being accepted as showing here, attach is, and there is no indication from the core network that CS fallback, for example, is preferred, CS fallback is not preferred. So what we'll do, the UE will check this kind of message, which is the network capability, whether it's being supported or not, IMS VoIP over PS. So a UE checks for IMS voice PS session supported or not. If it's supporting, then it will, if it's not supported, it will use CS fallback. But in case if it's being supported as showing here, it will use directly the IMS-PS voice, which means a VoLTE call. So it's dependent on this message. So in case if the attach is being failed or not accepted by the network, again the UE will go and check the capability of the network. So if assume that the main network mentioned that it's not being supported for it's not supporting to have IMS-PS. So now this is the second piece of information will come into the figure, which is now the UE will check, the network will check this kind of information, which is, for example, centric. If the UE checks first his voice centric or data centric. So once the UE check this part, for example, he found that he's voice centric, so As long as the IMS is not being supported, he will select back to other RAT, for example, to 3G. But if it's data centric, means he cannot initiate any calls, so we'll stay in RAT and in the same technology, which is, for example, the 4G, and the call will fail. So this is the overall flow, and you can find all the details about this, the remaining four, if you'd like to go through details through this kind of version 3GP. So now let's move to the next part. So once the UE completed his attach, the first attach, after that, as you can see here in the top left here, the user completed already the attach, which is using the PCI 619. Now the user need to initiate another attach or another BDN connectivity request, requesting for the IMS EBN, and also he would like to get the proxy CSCF IP for the IMS in order to be able now to start the IMS registration. So actually here in the top right here, the right and the further right, this is end-to-end call flow. It's exactly same, almost the same as the registration. For example, initially you will send the BDN connectivity request, requesting the IP address of the proxy in this particular message. I will show this one in the next slide in details. So requesting that I would like to get the proxy CSCF IP in order to be able to communicate with the IMS network. Then again, the MME will start following the same process which being explained in the 4G attached message. It will send create session request for the serving gateway, which is including again the tunnel endpoint, and also adding the information about the BDN type, IP, and also requesting the, which is the most important here, requesting the proxy CSCF. And this message will be forwarded to the BGW, including the same information. Then here there will be something called IP CAN between the BGW and PCRF. The IP CAN actually it's abbreviation for IP Connectivity Access Network. And the BGW is just asking the PCRF, okay, now we would like to get the information for the ABN, which is IMS PCI 5. So I need to the BCC rules, and the quality of service information about the PCI 5. So the BCRF will be responding with this kind of information. Then after BGW receive the response, it will send create session response to the serving gateway, which including the information about the IMS ABN and the PCI 5 information, and also the information about the IP of the PCSCF in general. And also it will sending, if you remember, we mentioned that the tunnel endpoint for the GTB. So it will for its own tunnel endpoint in order to create the new tunnel or new GTB to call between the serving gateway and back 5 for that part, because we need a new tunnel endpoint for the QCI 5. The first one was QCI 6 to 9. Then it will follow exactly the same what we have mentioned before until it's being complete. Then actually what I would like to discuss with you in details, it will be about the BDN connectivity request, what kind of information which we have it here, and how the UE is getting the information from the network, as we just mentioned here, and what is the message content. So let's move to the next slide. So now let's see what we have as the content of this message. For example, here, the BDN connectivity request, if you open this message, you'll find in that part, it's showing that the UE is requesting, okay, I would like to get the information. First, my BDN type, I'm supporting IP version 4. And here, this is my access point name, which I would like to get information about it, which is IMS. Then within this message, you will find also that the user himself is sending proxy CSCF IP version 4 address request. He's requesting, I would like to get the address of the PCSCF, which is, if you remember, this was the first point of contact for the IMS, and the user would like to get that part to start doing this third step, which is the registration to the IMS. So here it will be sending the request. Once he receives the response from the init B or through the steps which we just explained previously, it will say he will receive this activate default ABS period request. And within that part, you'll find that it's having information about the IMS now and the quality of service, and also it will give them the address now. It will tell them, okay, this is the proxy CSCF IP version 4 address. You'll find the address here. And this is usually they call it proxy CSCF discovery. So now the user he's aware about the IP. He can start communicating with the IMS in general to start doing the registration to the IMS. So after that part, the user will start doing the registration, which will be our next part. We'll discuss about the end-to-end call flow for the registration, and also the signaling contents of the registration. So let's move forward. So once the users got the PCSCF request IP address, now he can start communicating with the network. So the first on the left here, this is the user himself. This is the UE. So the user now need to get SIP registered or make the registration for the IMS. So the question which you might ask yourself, why the user need again to do registration or attach to IMS? Actually, the IMS even the registration or the attach being completed for the EBC side. For the IMS itself, the user is still not being authenticated or authorized to access the network. He needs first to get registered to the IMS. So here we are going to explain. As you can see here, the first step, what will happen? The user will send a SIP register message to the PCSCF. If you remember in the previous session, we were explaining about the function of the IMS entities. We mentioned that this proxy CSF is actually acting as the first point of contact. So all the messages need to go through the PCSF first, through the UE, then it will be forwarded till it reach the C. I added in the top right here what is CSCF abbreviate stands for. It stands for Call Session Control Function. So the first point of contact, again, as mentioned before, in the function of the IMS, is that the proxy call session control function is acting as a first point of contact. So it will receive the SIP register. The SIP register, actually, includes many important information. I will go through them in details in the next slide. But just here, I will just give you a high level what kind of information which is mandatory to be known by the proxy CS. The first information is two pieces of information. The first one is IMBI, IMBU. This one, actually, the first one is abbreviated for private user identity, or IMS private user identity. And actually, this is used for the authentication and also internal working within the IMS itself. So this is like identity, but it's a private one, which is used by the IMS. The second one stands for IMS public user identity, and this is like for any external communication between the IMS entities and any other entities. So the first one is similar to the MZ, for example. So yeah, this is the main idea. The third information, the UE is telling the PCCF or the proxy call session control function its own IP address. It's telling this is my IP address, where whenever you would like to send any response or any feedback, you need to send it at this particular address. So now the same information will be forwarded from the proxy CSCF to the interrogating call session control function, which is IC. The main idea that actually it cannot be forwarded from the proxy to the interrogating directly, because still the proxy doesn't know what the IP address of the interrogating CSCF. So the proxy call session control function need first to query the DNS, asking them about asking or getting the IP addresses about the I-CSCF. So once it's got the IC using the SIP URI, which is being included in the SIP register, what is being sent to the DNS will be now telling them you can send it to this particular IP address. So it will forward the same message here. Then the I-CSCF actually need to do what? It's need now to go and query from the HSS, home subscriber server, about the IP address of the serving call session control function for this particular user. So it will send this user authorization request. And as you can see in the top right here, this is requesting for the authentication information. And the second part is requesting for the information about the serving call session control function. Actually, what is this authentication information? This one actually it's telling them that I would like to get the authentication information for this IMBI and the MBU, giving this two pieces of information to the HSS, asking for this kind of information, which means that what giving them the IP addresses or this information, that asking them that what is the S-CSCF serving this for this particular user. So now the one this being done, that will respond back to the ICF, giving them the address of the serving command control call session control function. It will sending this SIP register, and now the ICF knows where is the serving SCCF where. For example, assume you have in the network 4 serving call session control function. So the HSS will tell them that this particular user is serving, for example, can be served by the SCCF1 or 2 or 3 or 4. So this is the main idea why the interrogating CSCF is invoking or interrogating the HSS to get the information about the serving call session control function. Also, other important information that the HSS check, not only the serving command control session function, it's also taking this IMBI and MBU to check that this user is authorized. Maybe the user is restricted or blacklisted or whatever. So this is just a confirmation also of the information which is being communicated to I-CSCF. So once he received the address, it will forward the same information from the ICF to the serving CSCF. Then the SCF actually will check this user is being authorized to access the network or not. As you remember, and also the function which being mentioned in the previous video, that one of the function of the serving call session control function is to do the registration or complete the registration for the MS for the users. So now the serving will send multimedia authentication request to JSS, and this will include a piece of information also for the user identity. Ask them, please give me the authorization vector of this user. So actually what it means by authorization vector, what kind of information it's requesting the HSS to provide. If you look into here, the authentication vector is actually consisting of 5 points. First one is random number, and this authentication vector, and this is the network response, something called X response, and the ciphering and integrity keys, which is being required from the this all information will be including in the multimedia authentication answer. Actually, this is authentication called authentication token, and this is usually generated by something called master key. And in summary, this information just being used by the S-CSCF to start challenging the users about his authentication is being able to access the network or not. So it will send this kind of information to the I-CSCF, then it will be sent to proxy CSF, but the proxy CSF will filter out this information, especially for the they call it CK and IK, which is a ciphering key and integrity. It will just it will be saved within the proxy CSF, and it will just be forwarding these two information, which is user identity and the random here. Then what will happen? The user now will add some information. He will send in the SIP register his own response called signal response, which also the user is what the user is doing. Actually, the users also can generate his own authentication vector and through something called master key. So he will compare whatever being received from the SCCF with the one which is being generated by the users. If both are equal, this means he's authorized. So he'll send again a new sub-register, including his own response that yes, authorized to access. He will send this one, which is called signal response. And also, again, he will include his UIB address, asking him, please send me the feedback at this IP address or the acknowledge at this IP address. Then this message will be forwarding. And the last step here, the SCF, once receive this information, he will compare this RES, which is signal response, with the X response from the network. If both are equal to each other, then this means the user is being authorized. And the last step, that now the serving call session control function need to inform the HSS to update its own database that I will be serving these users all over the way for the meantime. So it's just asking them to update the information and to restore the new information that I'm the one who's going to serve this particular user. Then it will be just sending acknowledgement to the user. So this is just the end-to-end call flow. Now let's go through the details about the SIP register message, which is contain very important information which you need to understand about it. Actually, here I just take the figure which is the endpoint for between the user and proxy CSCF. And here we'd like to go through the details, especially for the SIP register message. You can see in the bottom left here where we have the from the drive test, or even from the if you have prop, or if you have prop, I mean from traces being captured from the IMS site, so you can check from the Wireshark, you'll find the same information. So here you have four information, as you can see. The first one was the first SIP register, which is this one. Then you will have the response, which is 400.01 unauthorized, which is the proxy or the serving CSCF is challenging the users. Then it will have the response from the users. Then again, it will be ending by 200 OK, which is acknowledgement, which is telling the user now you are registered to the IMS network. So let's explore quickly what is the IMS SIP register information. Let's zoom in here and right here. If you zoom into this part, you will find that first part here in the SIP register, first SIP register, it's having this register message, which is actually meaning that, okay, this user is sending, now this is just telling them that I'm trying to register to the S-CSCF, so it's sending this request to the P-CSCF. And as you can see here, this is including many information as a method. First, the method H register, I would like to register to the IMS network. And after that, it's just giving you that the SIP URI here, which is IMS dot, for example, mobile network country XYZ, MC XYZ. Then here, this is SIP version, which is SIP version 2.0. So this is just in summary, this is just telling the PCSF I would like to register to the net. And the second one is via. Actually, this is just including the IP address. If remember, we mentioned that the user need to send his IP address to the network. So the IP address here, just telling them, please send me the response at this particular message. Then here you have something called maximum forward. This is actually, it's just telling like how many, what is the maximum number of hops you have it here. What it means by maximum number of hops. For example, as you know, the user initially will send the register message to the PCSCF, right? Then the PCSCF need to forward this message to I-CSCF, which is interrogating. Then again, he need to forward to the serving control or serving S-CSCF. And this is actually, each one of those is counted as a hub. So just the network is telling him, he knows that the maximum hub, he's telling them that maximum hubs you can take is 70, for example. This is not usually not looking into that much. And this one, BX is network information. Actually, this is just including information about the serving cell identity and also the RAT. For example, he's scamming an FDD, and this is the cell ID, which is telling them about his own information. So this, then the from one, this is just telling them about the IMBU. If you remember, this is the identity of the sender, which is IMS public user identity. This is also one of the information which is being sent. And the same for two, just telling them about which one you would like to call, and this is a public or IMBU for the mobile terminating, or the, you can see EUEB. Then you have something called C sequence. For example, here it's showing as one register. This is indicating to the network how many times you send that sub register. For example, assume he sent one sub register initially and it was not successful, he initiated another one. So this one will come as 2. If it's failed, you will send another one, which will be coming as 3, for example. Then you have this kind of information within this contact. This is showing you the IME, so you can get the IMEI for this particular user from this information. Then here there's something called expires, and this is very important information. This is very, very important because actually this is, as somebody is telling you what is IMS registration period. What it means by this? It means this is in second. For example, this 80,000 second. This means that the user need to renew his registration before the expiry of this timer. So in case if the user didn't send a renew, for example, assume that he's out of service or whatever, then the IMS will deregister the users from the network. So this is very important also during the troubleshooting. And also some of the information before that part. For example, this is the contact here. This contact actually is telling that this is the UE address. It's telling about his address, his own address. And also one of the information under the contact one here, you'll find that this is here is saying that IMS ICSI MMTEL is just stating that I'm supporting the services for like the MTAS, and also, for example, the SMS over IB. Here, this is kind of information is being stated here, but especially for the MMTEL, as mentioned here. And here this is already being discussed. Then the last one, which is about the authorization, which is actually very important, is you can see here in this authorization there is something called digest username. And this one actually, digest username is including the IMB, which is user private identity. And here it's informing them that, okay, this is the address of the S-CSCF, for example, authentication center, which I would like to access, or I would like to get authentication, or I need to get authentication from the S-CSCF. Then it will be ending by this nouns. This will be later on also in the save register message, second one, or the 401, where the user will start comparing the information received by the network with his own information to confirm he's being authorized to access the network or not. So this is just in general what we have in the save register. And now the next one, which is about the 401, for example, unauthorized. This one will just containing something called nouns and other information, which just giving the information was being mentioned, for example, the numbers and random numbers and this kind of information, where the user need to compare to his own numbers to make sure that he's being authorized or not. He will compare. Once it's being equal, he will be sending a response back to the network or the sub register, which is a sending response about his own, as we mentioned before, signal response. As I mentioned before, the signal response that, okay, this is my response. After I compared, I found that I'm authorized to access the network. And once it's received from the serving CSCF, it will compare the same, and it will reply back to the users that, okay, with 200K, now you are authorized. So now that's what's being done. Now let's move to the last part of this session, which is really, really very interesting part. So the last part was covering the end-to-end high-level call view. So let's go through it and see what we have. So here we're going to explain the high-level call flow of the mobile originating. This is very important. So assuming the network now you have user A, okay, and user B. First one is originating and second one is terminating. So the first part here, you can see it's classified here. This is originating IMS, and this is the terminating IMS, and this is access network, which is the ABC and the E node B and so on. So the first thing the user will do, he will be sending the SIP invite, right? So the user will initiate the SIP invite message. So what kind of information will be included in the SIP invite? We'll go through the details later on in the next session, but just as a piece of information you need to know, there is two kinds of information in the SIP invite. Something called the SIP part, which SIP part includes signaling and the signaling procedures. For example, it includes the URI of the SIP, the user B, is telling them, for example, this user B and the URI, for example, his address is for example, www.google.com or whatever. This is the first part. It's telling them about the address of the user in mobile terminating. This is and also it's telling them about its own address. Also, it's telling them this is my IP as well. You need to send the feedback at this particular IP. And the second part, it's about the something called SDB offer. What it means by SDB offer? Actually, when the user mobile originating initiate the calls, he need to state what kind of media type we have. This SDB offer is very important. SDB offer is telling them what is the media type, having two information: media type and the codec. What kind of codec being supported? So what is the media type? I'm telling them, for example, this is a voice call or a video call, as an example. So they assume that the media type will be saying that this is a voice call. And the second part, it's about the codec. Just one very important information: the user the negotiation will be happening in the call setup, during the call setup. So the MO users will announce that I'm supporting this kind of codec ranges. For example, I'm supporting wideband MR from 12.2 to XYZ, or I'm supporting narrowband and wideband, and they will give all the supporting codecs by the mobile originating. So this is called SDB offer. So this message will be forwarding for the proxy CSCF, and as I mentioned before, proxy CSCF is the first point of contact. Then the CSCF will forwarding the same information to the serving SCCF, right? And now, if you remember, we mentioned one function of the MTAS. The MTAS need to, why the SCSF is sent to MTAS? Because if you remember, we mentioned in the previous session also that the MTAS in general is handling the MO and MT call establishment. So what will happen here actually? The SCCF is for this one to MTAS because it will ask the MMTEL or MTAS what are the originating service are allowed for this users. The MTAS need to check if this user is allowed to originate a call or not. For example, is it possible that user is being barred from originating calls? Or, for example, the user found that his credit or his balance is being, he didn't pay his bill. So he's not, for example, authorized to make originating calls. So if he's authorized to make a call, the next step will be that the SCF now need to go and make a query within something called entities called DNS and the enum. DNS is referring to domain name system and electronic number mapping for the enum. Actually, the main idea, if you remember, in the same invite, the user didn't send the IP address for user B, right? So still the SCF doesn't know what is the IP address. It doesn't know where it can send this kind of information of the same invite, right? So it's invoking or asking the DNS and the enum to start performing the query on the NIS based on the UB home. For example, this was a home domain, ub@yy.com. Then the DNS will resolve with terminating I-CSCF IP address. So this is the DNS main job, which is referred to domain name system, is to resolve this domain into IP addresses. So actually, now this is the job of DNS. What about the enum? Enum actually it's can do something similar through that within the same invite. You will find also that the contact number of the mobile terminating is being shared. For example, the number of this user is being shared. So the enum actually what it can do, it's like a protocol that maps this telephone number into internet resources. For example, it will map it into also IP addresses or something called SIP URIs. Tell them that this is the uniform resource identifiers. This is the URI, SIP URI. So both of them actually work together with the enum and DNS to facilitate the translation of the phone numbers or the domain or the domain, okay, into IP addresses and or CBURIs. This is the main idea about the DNS and the enum. Just in summary, to resolve this UE number or the UE domain for the terminating calls into IP addresses, so the SCF will know where to forward the same invite. Then the SCF will forward, once it got the IP addresses, it will forward this the same invite to the I-CSCF or the interrogating CSCF for the originating network, asking them please start finding this terminating IMS for the, especially for the serving SCF for the terminating users. So if you remember also one of the function we mentioned in the previous session, that one of the function of the interrogating CSCF, it's working whenever there is an incoming call, especially from two different networks. It's working as the first point of contact in case of incoming call. For example, the originating call, when you initiate originating calls, the first point of contact was the proxy CSCF, but the incoming call, it will be the terminating I-CSCF. So the terminating I-CSCF will send to the message, the same invite to the ICF, asking them, please, I would like to know where is the SCF for this network. Please interrogate and try to find the which SCF is being served in the network. Again, it might be there is 4 SCSF, so it need to know which one we need to send the SCF. So once the terminating SCSF interrogating the CSCF receive the call, it will just what it will do. It will go and query from the HSS. What queries make it ready to confirm what kind of which SCSF is being served by the MT user B. So it will tell them that the S-CSCF is, for example, number 1 or number 2 or number 3 and so on. So once it's being known by the ICF, it will forward this one for the ICF, S-CSCF from I to S, and it will follow the same procedures. For example, again, this one will go and query on invoke the MTAS, asking them whether this user is being able to receive a calls or not. So this is the same steps to just check whatever being done for the originating. The MTAS will do the same. That's why we mentioned that the function, it's the MTAS is supporting both originating and terminating call establishment. Then once being confirmed, then the SCF will be following the same invite to the proxy CSCF of the terminating users, and now it will be following again the same message here. This will be routing here, and now this same invite will be including the user B and his current IP address actually, and the SDB offer which is being sent from a user. For example, the A user sending this is the media CS call, and this is my codec being supported. Now what needs to be done from the user B? User B actually now need to check and send his also SDB offer as well, which is his codec. He needs to say, I'm supporting this codec as well. This is a codec negotiation. So he will send, for example, I'm supporting narrowband. So both of them will check. If both of them supporting, for example, the highest codec rate, so the highest codec will be selected. And for example, assume that user A was supporting MR wideband, while user B supporting only narrowband. So in this case, narrowband will be selected. So this kind of negotiation to check what is the capability of the codec for both of them. So now the user B need to send a response, which is actually called something called the 183 progress, which is usually include the SDB answer. And this is telling them this is my supported codec, and this is a provisioning response, which indicates what kind of coding is being supported. So it will again move back until it's being received by the users here. It's being above here. You can see it's received the 183 session progress SDB. So you can see now the blue dotted line. This is the sequence, which is usually the signaling will be followed. But all of that, till now, the call is not, the dedicated beer is not being established. All this was passing through the KCI 5, right? Which is a default ABS peer, which is only for the step signaling, right? So once he received this offer, will be another response. We'll be discussing details in next sessions. For example, sending the response and so on. But assume all the steps are being done, ringing being sent and so on. Now, in between, the dedicated bearer will be created between the user B and user A, which is through the KCI1. And now the RTB media can flow directly from the user A to user B through this access network through the KCI1. We'll explain in details how this can be done. So the RTB media is established directly between both of the users using the agreed SDB offer or parameters in general, which means in summary what kind of codecs being supported. So this will be transferred over here. Hello everyone. Welcome to the third session of the end-to-end training campaign. In today's video, actually, we are going to cover these three main points, which is related to the end-to-end call flow and signaling content. But we'll try first to recap the VoLTE protocols and the SIP description general, just to have high-level introduction and high-level understanding about it before digging into the details of the end-to signal. Then we'll be ending by going through the contents of the end-to-end call flow. We'll go through as much as we can and explain the contents of the messages to make it more clear for you about how to do the troubleshooting and analysis if you understand the signal contents. I suggest if you didn't watch the previous two sessions, to go and watch them first before watching this one, because it will make it more easy for you and it will facilitate your understanding. So let's move forward for the next slide. So actually, initially, I would like to start with you about the VoLTE protocols and the interfaces as well. First of all, that in VoLTE there is two main protocols. This is them two main, or they call it the core signaling protocols used usually in IMS, which is actually the diameter protocol and the SIP protocol. The SIP, the diameter in general is using to, as mentioned, need to authenticate or authorize or even provide accurate billing information. And as you can see, diameter is usually between, for example, the HSS and the serving CSCF or the IMS in general here. And here is, for example, every time the SCF required to get some information about the user, he will go and inquiry the HSS. And even though the between the HSS, for example, and the other entities in the ABC, this is also using diameter protocol. And also it's being used between the PCSCF and the PCRF. And this is like in case the PCCF would like to do provisioning for the quality of service and so on. So it will query or request the PCRF to start. So this is the protocol used, which is called diameter protocol. And for the SIP protocol, it's just used to establish and control the real-time data. For example, if you'd like to have signaling messages and to start establishing all the SIP signaling until you get the dedicated bearer activated. So this should be done through the SIP protocol, which is actually abbreviation for or stands for Session Initiation Protocol. And also there is a very important one, which will be covered today in details. It's called SDP. This is called Session Description Protocol. And this is usually you'll find it within the SIP invite message. Within the SIP invite, you will find two parts actually. The first one, which is called SIP part, which is including the signaling, and you'll find something called SDP, which is Session Descriptor Protocol or Session Description Protocol. And this is just include information about two pieces of information, which is the first one about the media type. For example, this is going to be a video call or a voice call. This is one of the information. And the other one, it's about the codecs supported by the users. For example, in the same invite, they call it SDP offer. For example, the MO users will be sending the SDP offer for the MT users, telling him, this is my supported codecs. I'm waiting for your response with SDP answer. So later on, the MT users or the terminating users, you need to send back SDP as well, but it will call SDP answer. Also, it will be including the supported codecs. Then you will start negotiating until you reach into a common codecs between both of them. And the last protocol is called real-time protocol, and this is usually used to carry the traffic, which is media, and this is usually carried all through the dedicated bearer. And there is one protocol also between interface and the protocol between the users and the MTAS directly. It's called U2 interface, and it's using a protocol called XCAP, and just this is using for the supplementary services as mentioned here. And if you'd like to get more details, you can just refer to the HBB about this point. So now let's move forward for the next part. So now let's go through the second part, which is related to the SIP messages. Actually, then the SIP messages, I will try to go through the high-level description or high-level introduction about the SIP messages before we jump into the end-to-end call flow. Actually, SIP messages, we can classify it into two parts. First one is called the SIP request, and the second called SIP responses. And this SIP responses is classified or categorized into two things, which is the provisional and final. Provisional means that sometimes that you would like, for example, to do provisioning or inform the other side of the call that, for example, I would like to, this is my codecs and I'm waiting your confirmation, or you're alerting, for example, through 180 ringing. So this means all the time you will be waiting for a response, which is called final response. So provisional means that all the time it must be acknowledged by something, right? Which is the step response, even successful, which is the 200 plus, or for example, the other steps, which is from 300 till 600. So now let's go quickly through the main messages, which is actually will be more explained in today's session. So let's, for example, go through the first one, which is the register. We already explained about this part in the previous session in details for the end-to-end call flow about the register. Register in general, it's being sent by the client or the user in general, just to requesting to, I would like to register to the S-CSCF, right? Or the IMS in general. He would like to register to the S-CSCF to start, for example, sending the same invites and start making the calls in general. And the same invite, it will be sending from the mobile originating call the client whenever he would like to invite another user to start a call, or he would like to call another user. So he'll be sending SIP invite. Actually, the SIP acknowledgement or the acknowledgement, this is usually comes at the very end of the call and in the context of the SIP invite from the client or the mobile originating. Whenever he's acknowledging, yes, now I can, after he received the 200 OK after 180 ringing, just sending acknowledgement, yes, now I can start the call. So this is the last final message, and we'll be discussing this in details. And the highlighted, two highlighted, this is also very important. The SIP update, this is actually usually sent by the mobile originating device. This is whenever you have this kind of things called precondition. We'll be discussing about this precondition, but in summary, preconditions means that the terminating users cannot send 180 ringing until he receive a confirmation from the mobile originating call that he has already established his media or his dedicated bearer. So this is information will be sent through the mobile originating through the update message, and this is just indicate that the preconditions has been accepted and the media is now active for the mobile originating call. This is what it means by the update message actually. The BRAC, actually this is called BRAC 183 because this is usually a response for this message was called 183 session progress, and this is message usually sent by the mobile terminating call, which is include the SDB answer or SDBS answer from the B side, which is telling the mobile originating this is my supported codec ranges, so it's being sent in this within this message. So this is like acknowledgement from mobile originating for this particular message. Actually, this is the main message highlighted here, which we discussed today, but let me quickly scan these three messages as well. This is by message actually in case, for example, the users already won't like to end the call. So this by message will be being sent. And usually the by message can be also during any failures, and usually it cover the cause. For example, if the user is initiating the call, it will be showing as showing here. For example, that this is user trigger. The user triggered to cancel or to end the call, sorry, to end the session, and he would like to clear the session. So it will be sent as SIP message SIP by, so it will be SIP called user triggered as a reason. And the second one, it's about the SIP cancel. Actually, this is in case, for example, assume that the user already initiated SIP invite, but before it's being responded or before it's being receiving response from the mobile terminating, he would like to cancel the call. So he will send cancel the call. So this SIP cancel will be sent at the end. And now let's go quickly through the provisional messages as well. For example, this 100 trying, this is just usually sent by the server to, for example, if the user sends 7 invite, it will be responded by 100 trying, telling him, please don't send a new request. I already received your request and I already started the provisioning and I will get back to you soon. And 180 ringing is usually sent by the mobile terminating to alert the originating or the mobile originating call, mobile originating terminal that I already now start ringing. And 183 session progress we already discussed. This you usually send by bulk terminating includes something called SDP answer, which is including the codecs supported date. And quickly for that part, any 200 messages, this is means it's the message is being successful. For example, 200 OK, 200 OK 7 byte. This means your request is being acknowledged and successful. And this is, for example, 300 redirection or redirect. This is usually when the mobile originating sent to a wrong server, or let's say that this is not his server. So the server, for example, server 1 and server 2. So server 1 know that this request should go to the server 2, so it will reply back to him, you should be redirected to the server 2, and so on. And you have this 500 server failures. This is indicating that there is a failures. For example, there is something called 504 and 503 server internal error or and so on. This is indicating that there is a problem in the server. So this is like a response from them. And there is 600 failures. This is indicating there is a global failure that many terminals is facing the same issue. And this is also 400, including the explaining that there is a problem in the client. For example, client mistake. For example, let's say assume there is one common one which is called 486 busy here, which means that the terminal is busy and he cannot pick the call. So this will be sent for the mobile originating call from mobile terminating or from the IMS to the mobile terminating. Which means in like 486 means that the user I'm calling is currently busy. So now let's move through the end-to-end call because this will take some time. Before I go to the end-to-end call flow, which is including both RAN and the EBC plus the 7 byte. I would like just to explore first the end-to-end SIP signaling, because this is like to make it more clear for you. Usually you will see most of the messages or the explanation between the UE and the proxy, and this is also fine, but I would like to take the complete flow just to explain what's happening. So the first thing the user will usually do, he will send the 7 byte message, and this 7 byte contains two important information. It will be sent first from the mobile originating to the proxy CSCF, which is acting as a first point of contact. This is including two very important information, which is having the first of all the media type, which is, for example, indicating that I'm doing a voice call, not a for example video, and also my codecs is XYZ, for example, and this is called SDB offer. My SDB offer is voice call plus this is my codec type. Then it will including some information, for example, the IP and the phone numbers from the originator terminating, just to get some information from proxy, which device I'm going to call, and what is my IP whenever you are going to send back a response to me. So directly the server or the P-CSCF will reply 100 trying, and this is the main cause of that part, that just sending that, please don't save any save invite. I already received your request and I start already progressing your request. So don't send any new sub invite until I get back to you. Then the same message will start be forwarding to first part to the S-CSCF of the mobile originating. And as you know, during the registration already the serving PSCF already known by the user and the proxy. So it will be directly send this part. But the first thing the SCCF would like to do, it just would like to confirm first this user is capable to make originating calls or not. For example, there is no any restriction, he's not barred, he didn't finish his credit, and so on. So it will go and query or invoke the MTAS, as you can see here. It will prompt the MTAS for originating service to confirm that the user is capable or not. And for sure, every 7 byte will be responded with 100 trying. And the main cause again, that reason for 100 trying, that to tell them, guys, please don't send new 7 byte. I already received your request. So now that will prompt it. Once it's being confirmed, the SCF will go and query the enum, as you can see here, and it will have, please query the enum, please find the user P location or domain name. I cannot find, this is the information for the user, please translate it or resolve the number into domain name or the example IP address, which is including the DNS also might be a part of this process. So this is a main function, and we already discussed this in the previous session. Once he got the information about the user B location or the terminating, now the SCF will be communicating, will sending the same invite message to the interrogating SCF for the terminating. And as we mentioned, SCSCF is acting as a first point of contact for the incoming calls. So it will be the first point of contact, and this is opposite to the proxy for the originating acting as the first point of contact. So now the same invite message will be forwarded from the SCCF to interrogating CSCF after the enum told them the IP address or the location of this particular user. So 7 byte will be going again, 100 trying will be coming back, but the ICSCF now doesn't know this user is served by which serving CSCF. So now the ICSCF will need to query about the information which is being shared here for this user information from the HSS to ask him this user is served by which CSCF. Might be the network having different SCSF serving CSCF, for example, 4 or 5 or whatever. So it will be sending check, please tell me which one is being serving this particular user. So it will tell him, for example, SCSF number 2 is serving this particular user. So now the ICSF will forward the same invite again to the same part, and it will directly be replying by 100 trying. And again, the same step here. The CSF will go and prompt or invoke the MTAS, asking him whether this user is capable to receive a calls or not. And about, for example, there is no problem in his bills and there is no problems for any restrictions or not barred or whatever. Once it's being done, again, now the invite message will be forwarded directly to the proxy CSF and it will be coming back. And once this is being done, now the proxy will be forwarded to the users, and now 100 trying will be done. Now, once the user receives the 7 byte, which is including the SDB, again, remember, keep this one in mind, commonly called SB offer, which is session descriptor or session description. This part actually it's calling again the media and the codecs type. So now the user need to inform this particular user that now I need to answer to you. I need to send you SDB answer, which including my supported codecs as well to start the negotiation. So this message actually once it's being received the proxy, this message including the supported codecs, the proxy will directly start activating the dedicated bearer for this particular user. So it will be starting communicating with the EBC. Please now start initiating the for example, first it needs to, for example, to communicate with the PCRF, with the policy and charge center, just to start make the provisioning. This will be going details. It will, in general, it will, as summary, it will start the dedicated bureau for this mobile terminating. And it will keep this part, the 183 session in progress, like it will hold it until the dedicated bureau is being activated. Once the dedicated bureau is being activated, the proxy now will start forwarding the same message to following the same sequence which being explained from the S-CSCF to I-CSCF. Then again, it will go through the same process until it reaches the proxy for the mobile originating. And now once this message, which is called which is having the SDB answer, which is having the supported codecs by this users being received the proxy, now the proxy also will start invoking or requesting the EBC network to start activating the decoder bearer. Once the decoder bearer is being activated and confirmed, now this one will be forwarded to the device, which is 183 ring session progress, and now the UEA or the originating will receive the answer of the supported codecs. So he will compare both originating and terminating codecs, and he will take the common one. For example, let's say that the highest, if for example both supporting super band, for example, whatever highest one, it will be shared by both of them. And the codec usually it's taking the common one. For example, assume that one device supporting only narrowband and the other device supporting all EVS and for example MR wideband and narrowband and whatever. So it should take the narrowband because the terminating device only supporting the narrowband. So this should be something common between both of them. So usually try to take the highest one, but since the highest one, for example, the terminating is narrowband, so it will be narrowband being selected. So once this being done, now it need to send something called BRAC 103 as a response for this 103 message. And this message, are just to simplify it, it should go through the exact same sequence for the same invite, move from here, from UA to proxy, then proxy to CSCF, and so on. So it will send until it reaches the user. Then the user again need to acknowledge this message. So it will send back 200 OK BRAC. Then the user now will send something called update message. Actually, this flow is for the normal flow. Sometimes this is like assuming something called precondition zone. Preconditions means what? Preconditions means that the terminating users, if it's on, the terminating user cannot send 180 ringing until he receives confirmation from the mobile originating that his dedicated bearer or media is being now on or active. So this information will be communicating through this update message. Update message is telling the mobile terminating, yes, now the media is active for mobile originating. Now you can initiate the 180 ringing because now the media is active. So don't worry, you can now reply. So once you receive the update message, he will be responding by 200 OK update as a confirmation for that he received this message. Then directly will be sending 180 ringing. And now that there is a ringing between both devices, you can hear the ringing tune. And once the user pick the call, the user terminating, answer the call, he will send 200 OK save invite, 200 OK invite as a confirmation to the same invite message. Now that I answered the call, I'm waiting also your confirmation that you received this message. So the user will send the final messages called acknowledgement from the UEA to UEB, confirming that now the call is being established and successfully established. So again, this sequence, it might be different if you have, for example, precondition on or you have and so on. There is many different conditions. For example, sometimes you will find directly after receiving the same invite here, he will directly reply 180 ringing. Or sometimes you will see 183 session progress, but there will be no update message. It will be directly sent 180 ringing. So this is depend on the network deployment or the IMS strategy or the network strategy in general. But this is the main call flow, which the normal one, which is well known by everyone. So now let's move forward for the end-to-end one, which is including the same, but plus the radio as well and EBC. So now we'll go through again the same end-to-end call flow, but now including all the entities, but this is only for the originating side. Terminating will be explained in different session. And first, I will go through the signaling, then I will go through the signaling context for each of the messages being shared here. So assuming the mobile originating was already in idle mode and he would like to initiate a call. So the first process he would like to do, he will send something called RRC connection. He will start establishing his RRC connection. And in this RRC connection, he's sending like something called there's a nice message called service request, and this service request and the RRC connection request in general indicating that I would like to do a mobile originating code. I will show you the contents of the RRC connection request and which is indicating and also the service request, and this service request last message is piggybacked within this message was called initial UE message. We'll show the contents of this message in the next slide as well. So here the user is indicating, please, I would like to initiate a mobile originating call. So the MME will receive this now message. So now directly the MME will start initiating the context for this particular user. So it will send them initial context setup request, trying to establish whatever QCI default bearers, which is, for example, let's assume QCI 9 and 5. So it will ask the user now, it will ask the InnoDB to start preparing the context or activate the context for the default bearers, for example, QCI 9 and 5, because he would like to initiate a call and he's capable of VoLTE call or call over an IMS. So he would like to now establish his dedicated bearers. And every time the user is initiating in the 4G, initiating a request as a service request, he will all the time, the MME will establish both of them as a default bearers, which is by default called, maybe we call it always on for the 4G. So now the users, the next step that will have this security and UE capability information exchange, then you will have the RRC configuration message, which including the bearers and the quality of service of both of them, and trying to establish now the DRB, data radio bearer, for this particular user. And this RFC connection setup, including something called signaling radio bearer one, and this is including the information which would be used, for example, to start transmitting the subsequent messages, for example, which is the security and the UE capability information. And SOB in general used for NAS messages to transfer RRC messages and NAS messages. So this is also within RC connection setup. This one, as I mentioned, RC configuration will have the data radio bearer, including PCI 9 and 5, and also the signal radio bearer 2, which is also used to transfer NAS messages as well. So now the InnoDB, once it receives the confirmation from the user, it will initiate initial context setup response. This initial context setup response now telling him it's successfully being activated. But now they maybe need to communicate with the serving gateway to tell them, please now start activating again the paths of the downlink path towards the InnoDB and serving gateway, which actually includes the information received by the context setup response. This one was just including the InnoDB tunnel endpoint, which would be forwarded from the SMME to serving gateway to now start like creating the tunnel between the serving downlink tunnel between end-to-end tunnel between serving gateway and the InnoDB for the user plane. So the same message will be forwarded from serving gateway to packet gateway to complete the connection, and this is including the update as well about the default bearers which is being activated to the users. So asking them to modify their part and establishing S5, S8, and also the S1 bearer or the tunnel GTP tunnels between the serving gateway and InnoDB and so on. So this was the part of the initiating calls. We'll go through the messages in the next slide as well. Now the next part, once the user initiated the call, what will happen? Now the user is got the XI 5, right? It's now ready. It's being activated. So now he can initiate the first thing, which is the 7 byte, which is already discussed, including the SDB offer and the SDB body. Then it will be 100 trying, being response. Then from the terminating side, the proxy will receive the 183 SDB answer. This is coming from byte terminating. This is including the SDB answer, which is including the supported codecs, for example. Then now the proxy CSCF will ask the PCRF to start initiating the dedicated bearer. So through something called AAR, and this is AAR, it stands for Advertising Application Request, and this is including a lot of information, which is, for example, what kind of media is being sent by this particular users. So you would like to start the negotiation, and also the addresses of the UE and so on, and the supported bandwidths and the media type, for example, voice, and most important information is called flow status. Flow status is telling him that still the flow status is off, means still that the media is not being completed between both of them. Dedicated bearer is not yet being activated for terminating and originating as well. So this is just informing him that the media is still not off. We cannot transfer data now. So it will directly receive a response from the PCRF called the advertising application answer. Then the same message will be forwarded from the PCRF to the BGW, BDN gateway, which is asking the BGW to start provisioning BCC rules. And the BCC rules, like for example, it will translate this information into XI, for example, XI1. So it will ask the BGW to start initiating the dedicated bearer. And this dedicated bearer will include the XI1, MBR, GBR information, and ARP, and all the information to XI information. So now this will be directly responded here for our AIA, which is called a re-authentication answer, and the first one re-authentication request. Then directly it will send create bearer request from bucket gateway or BDN gateway to the serving gateway, asking them now please start initiating the quality of service. And this is the EBI, and this is my tunnel endpoint. Now he would like to create a new tunnel endpoint, right, for the XI1. So it's telling the my tunnel endpoint for the S5, S8 for the bucket gateway. This is my tunnel endpoint ID. So, and this is the quality of service I would like to create. So it will send the same message from the serving gateway to MME, and this one will include, it will add on top of it the serving gateway tunnel endpoint. Then it will, MME will take the same information which is being sent here. It will forward again to the node B, asking him, please now start activating the dedicated bearer context request. Even you will find in the traces Wireshark that this called ERA request, for example, plus the name, it will be between brackets that calling activate dedicated bearer request. Then the node B will send the same information, which is including quality of service for XI1 through the RRC configuration, including the DRB information for XI1 to the UE. Then the UE will, once replied, he will gain coming back ERAP setup response, then create bearer response, and so on. This is acknowledging the connection. Once being completed here, this means the dedicated bearer already being activated. So once the dedicated bearer is being activated and it's being confirmed here for the bucket gateway, now the SPC can now, or the P-CSCF can now send 183 session progress directly to the users because it's confirmed that the gear is being activated. It will send them this to the users. Now the users wants, because he already activated the gear, he can now reply with the BRAC as a response for 183 response. Then again, as we discussed, the side of proxy will receive a 200 OK from the terminating side. Then now the originating will again sending update message telling them, okay, because precondition was on, telling them now my media is on and I have already activated the digital bearer, so you can now initiate the call, or that you can now send 180 ring. So it will send a confirmation 200 OK update. I received your message. Now I will send ringing to you. So it will send before sending the ringing, you will, because this one already received 200 OK update, the proxy CSF from the terminating side. This is for the originating, received already from the terminating 200 OK update. So he need to, and he received a confirmation from the originating that the media is being on, right, or activated, the bearer. So he need to update the PCRF that now the flow status is on. Both originating and terminating has the bearer activated. So now the flow stats changed from off to on. So it will send these messages just as a confirmation. For the media, now it's being on. So now we can start having a flow or traffic flow between both of them. So directly now, the terminating will send 200 OK message. This one will be sent once it's being the serving P-CSCF will send to the UE the 200 OK as a response for this update message. Now the terminating will be sending for the P-CSCF of the originating the 180 ringing and 200 OK invite. 180 ringing first, it will be sent. Then after 180 ringing being sent, it will send 200 OK invite that I confirm, I answer the call. 200 OK invite come after the 180 ringing once the user pick the call. So the terminating pick the call. So you'll send after the 180 ringing, you'll send 200 OK as invite for the same invite, confirming. Once the user confirming that he sees the message, he will send now acknowledgement message, as you can see here, confirming the call is being established. Now let's go through the details of the messages. We'll take it one by one. First, I will split this end-to-end flow. I will take first the initiate VoLTE call and go message by message. Then we'll go through the next part, which will be more important about the information for the save invite and so on. So let's move forward. And before going forward, that as you can see that now just here confirming that RTB is now carrying and the queue is on, and now the traffic is being flown. So now let's move forward. So as you can see here, first I take only the part related to the initiate VoLTE call, which you already explained it, right? So I would like to take one by one, but this is how you will see the messages from the Wireshark. For example, here from Wireshark, he see all the S1AB and tell the serving gateway. So he see the initial UE message. And as you can see, the service request was coming from the UE is piggybacked with the initial UE message. Piggybacked because this was NAS message. So it's just sending through the initial UE message. That's why it's called service request. Then you have the initial context setup request. This is also including the UE capability information and asking for the UE capability information. For example, for this one, UE initial context setup request, which is this message. Then you will have the initial context setup response here, as you can see. Then after the modify EBS peer will be sent from the MME to the serving gateway. And here we have to, because we have two PCIs, for example, 8 and 5. So one will be for 8 and one will be for 5. So now let's go through the first message. For example, this, as you can see here, the first message, for example, the ROHC connection request. I just quoted from the 3GPP what kind of information you will have. If you zoom in here, let's move in here. This is both ROHC connection request and setup. The ROHC connection request, as you can see, it will having the STMZ. This is the most important, and also this will be the calls called voice call V1280. And the ROHC connection setup, which second one, will include information about the SRB1. So let me show you what we'll have in this information, especially for the second one, which is ROHC connection. As we highlighted here, the ROHC connection setup, which is coming here, is coming to establish the SRB1, which is a B1 will be used to transfer the subsequent ROHC messages. For example, the ROHC connection setup complete, and also the NAS messages, for example, the service request and so on. So as you can see here, for example, this message is called ROHC connection setup. Under this part, you will find SRB to add to mid list. Then you'll find the SRB identity, which is one here. Then we'll find all the related parameters for that part. For example, this is acknowledgement mode, use acknowledge mode. And this is the parameters, for example, the T-ball retransmission for the uplink, and also for the downlink, this is a retransmission. Then we go through, you'll find many other information related to the logic connect channels, and also you'll find another information, all the other information, which is very important. For example, if you open this one, we'll have the BE power, what is the power, and many others. For example, if you look into the antenna, it will tell you what is the transmission mode you use here, for example, transmission mode. So this is like sample from the content of ROHC connection setup. So now let's move to the next messages. So the next message, we need to explore what we have inside the initial UE message. So let's go. So as you can see, the initial UE message here, including the service request, right? All the service requests, and this is usually include this information, as you can see here. First part here, that having 6 items. It sometimes can be more, but this is the most common. For example, S1A APID. This is common. This is unique for this particular user, and it will be like it retain all over the call until the user go idle mode. It can be even used for filtering in Wireshark. It will filter all the AP messages for this particular user. Then here, this TAI, it will include all the information about the user location, tracking area update, MCC, MNC, and the CGI as well. This one will having the cell ID. And here we're having the ROHC establishment calls, which we showed MO voice, confirming that this is MO voice and the STMZ. And both this, if you remember, it was already included within the ROHC connection request. Okay, moving forward, next message actually will be the initial context setup request. And this will mainly include many information, but the most important for us is which ERAB you would like to set up. So here it will include the default peers, key size 9, for example, or 8, or 6, or 7, and key size 5 as well, which will be used for IMS. Asking the NLB, please now start initiating the context and the DRB, the data ready bureau for this particular user. So now, after that part, this part already will having the same information, so I'll not cover it again. I'll jump directly to the initial context setup response, and this is very important as well. This one will be covering first, telling them this is a successful outcome. It's being successful. And within this part, you will find something called ERAB 2 items, right? For example, here, which is ERAB ID 5, and also we have ERAB ID 6, for example, both of them will be sent in that part if you open the other one as well. And it will tell them this is my tunnel endpoint for ERAB ID 5. this is my tunnel endpoint for the E node B to take this part and forward directly to the modify EB and within the modify EBS request. And you can see here we have two modify EBS, one for example ERAB ID 5 and one for ERAB ID, for example 6, which is one for the XI 6 or 8 or and one for the other T3I, which is QSI 5. So this is information about the initial setup response. Now moving forward to the modify EBS peerer, as you can see, we here this one will having first information about the user location, right, with cell ID and so on, and tracking area update, blah blah, and all these kind of things. Then this is the EBI, which is 5. Also, it will have another one for the another QSI as we mentioned. Then it will forward tell them that okay, this one E node B GTPU interface. This is the tunnel end point for the E node B to now start having a tunnel between the MME and the serving gateway and the E node B. So it's telling him what was the tunnel endpoint from the E node B side as well, and this information will be forwarded again to the packet gateway. And once it's being done, it will be responded here and so on. So now let's move to the next part, which is related to the end-to-end signaling for the content from the starting from the invite message. So as you can see here from the same invite message here, this is the content on the right side here. First, as you can see here in the top right, this is actually the same invite will having a two piece of information. The first one, which is the SIP header or the SIP part, which is including information about the what is the device, terminating number IB, originating number IB. We'll go through the details here now. And the second word, which is called SDB part, session description protocol. This is we'll go through in details about that part. So the first part, it's about the SIP part, which we'll be having here. If you go this part, you will find first here in the top right here the request line. This is telling them this is my number and this is my network at this particular network, and this is for the terminating actually. I'm trying to invite this particular number. So this is a URI of the terminating number, which is including the number at IMS, for example, mobile network in Egypt or whatever indicating here. Then you will have this message header, right? The message header here will call via first. This via telling him that this is coming through me through the originating. So this is my IP, right? So this is my IP for the mobile originating call. Then you will have this maximum forward already explained. This is including how many hops you can go through. For example, you will find forward first to proxy, then SCF and so on. Then you have this route information. This route information includes information about the IP of the proxy CSCF and serving CSCF and name and information about for the mobile originating call. Then you will go through this contact information. It's telling him first of all my contact number from mobile originating is this my contact number, for example 987654321, and some information about the port number and so on. And then it's telling him that yes, I'm stating that I'm supporting the MMTEL or MTAS in general. Then the other information is important as well. Here it's saying allow. It's telling him that I'm supporting all these kind of SIP messages because sometimes there might be a problem in the SIP messages capability. So here it's telling him I'm supporting all these SIP messages, so I can initiate or receive or whatever for this kind of SIP messages. Then here it's stating that I'm supporting precondition as well, and 100 release. This is related to 183 as well. Just support precondition. I think that's a support precondition. Then the last part here is called B-access network information. This is having important information about the serving cell. For example, it's telling him I'm initiating the call in FDD. It can be TDD, it can be NR, for example. In the voice NR part, will be covering this part. And this is my cell ID as well. So this is the SIP, first part of the SIP, which is the SIP part. The second part now we'll go through it. It's SDB part, which is including the codecs. And this is very important because it will look like complicating in the beginning. So actually moving to the SDB part now, within the SIP invite, as you mentioned, we'll have SIP part already explained, and you have the SIP message body, including this SDB part. Now let's move and zoom in and see what we have. As I mentioned, it's first indicates that, for example, the media is voice, for example, as you can see here. It's telling him the voice is voice over IP. And here it's telling him I'm the owner. Here you can see usually the messages will not be coming like this. You'll find it as this between practices, for example, O or V or S or A, and they'll explain. This is the name of these sessions. the Wireshark translated like this. For example, this is telling him the SIP, the session description protocol version. The version of this DB is version 0. It's not that really important information. Then you will have this session ID. This is my IB network. For example, this IN received indication to IB network, and this is I'm using IB version 6, and this is my IP for the originating. And the session name, for example, I'm calling this mobile terminating or UEB, and this is called voice over IP, which is SSYB. I'm writing this by anything you see hash. This is my writing here, just to explain it. Then you'll have this kind of C here, C indication for connection information, and this is including the UEB address of the mobile originating number, and it's asking the network whenever you send a feedback or a reply, please send it at this particular IP version 6, and this is my IP. Then you will have the media description, and this is the most important. Actually, this is the most important part, that is telling them I'm going to make a media call audio, right? This will be a voice call, and I'm supporting 4 codecs. You can see RTB, AVB. This is related to the codecs. I'm supporting 4 codecs: 112, 116, 115, 118. Then it will split each one of those below here. I will explain to you now. Now it's stating first, audio means voice call, and this codecs means I'm supporting 4 different codecs. Now it will start splitting here. As you can see, first one, 112, you will find something called media attribute. Sometimes you'll find as A only. A means attribute, okay? So it's telling them that RTB map 112, for this 112, RTB 112, it's related to EVS, and this is the sampling rate, which is 16,000. So this is the codec type for this 112. It's EVS and 16,000, right? So this is the first type. Usually in the Wireshark, you'll find that you can open these messages and you'll get this information below it, but you can directly even read it from here. For example, this RT map 112 is equivalent to this one. EVS means this is your type, and this means your sampling rate. So EVS 16,000. Then here, this is media, something called again under the same message, media A, also attribute called FM. This is called RTB map. FMTB 112 as well. So still you are speaking about the same codec. This is just telling them that I'm supporting the mode change capability. I can change my capability, for example, for the codec, and I added the reference of 3GPP in the bottom right here. You can get that more details about this part. Then it will again go through again one by one. For example, 116, it will tell him, see here, attributes A, 116 AMR wideband 16,000, as you can see here. Then 115 again here, AMR wideband 60,000 as well. Then the last one, for example, 118, I'm supporting AMR 8,000. Then it will have some information about the channel bandwidth. The channel bandwidth is 50 kilobyte, as you can see here, and this is just integrating beat time, attribute beat time, that the packet time is 20 millisecond and the maximum is 240 millisecond. And the most important is called A, which attributes inactive, telling that the media is still not inactive. I don't have yet a dedicated bureau, so take care of that part. And here is saying that the current quality of service local none means I don't have any quality of service yet being initiated or established, and local for the serving, and whenever it's removed, this means it's terminating calls. Then here is saying that the quality equal DES, quality of service mandatory local send and receive, just stating that I'm mandatory. I'm telling you that I want to send and receive data. So this is just telling their or capability to the network. So this is the SDB part. It's very important to understand it. And here I just refer to the RFC for this particular part related to the capability of the media change, if you would like to refer to the details about the RFC number for the point which I'm mentioning here. Now let's move to the next message. Next message is actually, it's about 183 SDB answer. First, the SPC will directly reply with SIP, or the proxy CF will reply directly to SIP while on trying. This is just telling them don't send more any invite request. Then here, this is very important. They will receive the answer from the terminating calls, right? Which is 183 session progress, right? This is actually including the SDB answer. The terminating side will tell you about his supported codecs. For example, here he mentioned he's supporting coding 107 and 101, as you can see here. So 107, for example, is indicating that I'm supporting AMR. Let me zoom here quickly. is saying I'm supporting AMR wideband 60,000, and 101 is saying that this is that related to telephone number. So probably this will be the codec which will be both between both of them, because this is like the common between both of them. And here is also confirming that I'm supporting the precondition as well. So this is the SDB body for that part. Now what will happen? The once the proxy receive this 183, it will start initiating the quality of service, right? This AAR, as we mentioned before, it's including a lot of information. The first, and you can find this information in 3GPP 29.214, and the first part called service info status, just telling them that what is the current status of the media. And here it's just telling the media type. For example, the media type is audio, it's telling the BC, and this is the maximum supporting downlink and band requested bandwidth for downlink and uplink. I just quoted the downlink, but uplink was exactly the same. For example, he's mentioned here 49,000, just to tell him the information which he's going to make a BCC lookup to start initiating. Based on this information, he will start setting his BCC rules for the quality of service, for example, QCI1. And here is telling the flow status AVB. This one actually in this message, it should be off. But once you receive and the DKB is being activated for the originating, the last one here, AR, it will be now it's being enabled. So this will become at the end here. So this is information about the AR. Now the next one, actually, the terminating side will generate this AR after receiving the 183, right? This is just a reminder for that part. Yes. So now moving for the next part, which is AA, is just this is referring that this is successful. The diameter is being successful. I have received it and I have received successfully, just replying as a successful. Moving forward, actually, for the dedicated, once that this information moved from here to there, this exactly same information will be forwarded from PCRF to BGW, asking the BGW, now this is the BC rules. I would like you to start creating a QCI1 or dedicated bearer, or to create a bearer for the quality of service one, QCI1. So this create bearer request, as you can see here, it will have a lot of information. For example, the first one is EBI, telling him my EBI is 6, and this is the quality of service. And also it's telling here, this is the QCI1, and this is the bit rate for uplink and downlink, maximum bit rate and guaranteed bit rate, GBR and MBR for this QCI1. And also telling him my tunnel endpoint, which is S5, S8, is this. So it's telling the serving gateway as its tunnel endpoint. Then again, the create bearer request will be sent from the serving gateway to the MME. Then MME will send the inode B, the ERAP setup request message. And the ERAP setup request message will just include the information about the QCI1, which is already we're including in the create bearer request. And again, this one will be forwarded from the MME to the UE, which is again including the information again about the EBS peer identity, for example, what kind of XI1 information, for example, those for 7, and all the information about the data review bearer to start establishing this part. And once this part is being done, now the remaining will be continue for the messages. It will reply the confirmation here once it's being received from the BGW. Sorry. Once it's being the give is being established actually. So in between this is might be sent as well, but the mobile originating will receive now the 183 session progress, and we reply with BRAC. Then the terminating side will reply with 200 OK BRAC, will coming through the serving SPC or BCS. Usually they call BCSCF as SPC. So it will forward 200 OK BRAC, and because the precondition is on, so the other side will not send ringing until he receives the update message. So UE will send the update message as we explained. Once you send the update message, so now he will say the BCSCF will receive 200 OK update for that part, but first it will change the status flow from off to on, informing the BCRF that both sides now have been activated. And it will the BCSCF now, once it's informed the BCRF, it will further this 200 OK to this particular user, and directly the terminating side will send 180 ringing, telling him now I'll start ringing. And after it will send 200 OK invite. 200 OK invite means that he already picked the call, he answered the call. And once he send the answer the call, he will wait a response from the UE, which is acknowledgement for the 200 OK. And now this means the flow is being established between both sides, which is KSI1 is being established. Hi everyone. Welcome back to the VoLTE end-to-end training campaign. In today's session, we are going to cover the part related to the mobile terminating end-to-end call flow, and we'll just like try to address the differences compared to the mobile end-to-end call flow. And this part will be covering 3 points. The first one related to high-level view of the mobile terminating call scenarios. For example, the user, whenever he's going to receive the call, the mobile terminating, he might be in idle mode or connected mode. So we'll explain from high-level point of view what will be the network or user behavior in this current kind scenarios, either in idle or connected. Then we'll go through the end-to-end call flow, and we'll explore in details about the main messages for the paging and something called downlink data notification. I will explain this part directly from the word chart. I will show you what is the messages context which we have it, and what is the explanation for it, and also what kind of scenarios failures we might see in case of mobile terminating. And then within this part also we'll be covering some information, very interesting and good information about the 4G paging in general. So let's move forward. Okay, this is a high-level view of the UE states in case if the user is in idle mode or connected mode when is ever going to receive a call. So we'll go through both of them. But let me first explain something called ECM state. Actually, this UE ECM state, actually ECM refers or stands for EBS connection management. And this, like it's being this ECM state tell us whether there is an active connection between the UE and the BC or the core network or not, whether we have an active connection or not. What it means by active connection? Actually, active connection means that whether we have active EBS peer context or not. For example, the EBS peer, which is mainly for the default peer, for example, PCI 5 and PCI 1, whether it's being active or not. And in general, the EBS peer actually consists of 3 sub tunnels or peers. As you know, there is, if you remember, between the, let me show you. For example, as you know, between the UE side and the E-node B, there is a radio bearer, right? And between the E-node B and the MME, there is S1 connection, right? And this is, we call it like tunnel endpoint. And there is also another connection between the MME serving gateway, then between the serving gateway and the packet gateway. All the connection will be released in case of if you are an ECM idle mode, except the connection between the serving gateway and packet gateway, which is S5, S8 interface, which is a GTB tunnel between both of them. This will be retained all the time because this will be used in case an idle mode to notify the user. This will be explained in more details and whenever you go to the end-to-end call flow. So the ECM in general, as I mentioned, just it tells us whether there is an active connection between the UE and the core network or not. This is the main important point about the ECM state. And in general, the MME is responsible to track this kind of ECM state. Whenever the user moves to the idle mode, the MME will know. So it will consider the user in ECM state. So, and it will notify also the other entities, and it will start releasing the related interfaces or connection as we just mentioned. So now let's go through the both scenarios to just see what we'll have in case of the user is in connected or active. So I assume the user already in connected mode and he starts receiving the call. So in this case means that PCI 5 already active and the user already having PCI 5. So he can directly receive the invite, the SIP invite. He can directly receive the SIP invite message from the PC or proxy CSCF, right? It can be directly send the SIP invite message. So once he directly receive, because he have PCI 5 active, so he can receive all the SIP signaling as we mentioned in the previous sessions. So once he receive, he will be able to directly to reply with this 180th session, which as we explained before, including the SDP offer and this answer. And this SDP offer just telling the mobile originating that this is my supported codecs to start the negotiation about the codecs which is going to be agreed between or negotiated between both users. Then what's this being done? Then the network, once the network receive the 183 session, it will just start the procedures or process for to establish a dedicated bearer for the mobile terminating call. So this is a straightforward because the user is in active state or the connected mode, so he already have PCI 5, so he can directly receive the SIP invite. What about if the user is in idle mode? User in idle mode means that there is no bearer between the radio bearer between the UE and the E-node B, and also there is no only S5, S8 interfaces being there. S5, S8 interface, which is between the serving gateway and packet gateway. Actually, what will happen here? Because the user in idle mode, so the network will initiate something called initiate service request procedures or process. What it means by this, we'll explain this part in more detail now. This means the network will start now trying to notify the user that he have a call. So the first thing we'll do, as you can see, this is the overall entities which we have it. As you can see here there is a tunnel. This tunnel, in case of idle mode, which is between serving gateway and packet gateway, which we call S5, S8 interface, and this is the tunnel between them, it's retained active all the time, and also the peer context is being retained within the packet gateway and serving gateway. We just need to activate now the connection between the MME serving gateway and the MME and the BTS and the users, and also between the serving gateway and the user. This is what we need to do through the paging process or this network initiated service request. So what will happen? The first thing we'll do that the PCSCF will send something called a payload application, or in general the SIP invite message. It will forward the PCSCF proxy CSF will forward the SIP invite message to the packet gateway. So the packet gateway will start understand that there is a data need to be sent to the user. So it will send this downlink data directly to the serving gateway, as mentioned here. It will be sending the downlink data, and as I mentioned, the tunnel already activated, so it can send directly the data without no problem about that one. But now, what will happen? The serving gateway doesn't have any connection with the user, so it cannot forward this 7 byte. It cannot forward until there is a connection or PCI 5 being established, so it can forward this 7 byte message. So this data will be buffered within the serving gateway. It will buffer this data until it having an active connection, so it will proceed with the 7 byte. So what we'll do, the serving gateway will send something called DDN, which stands for downlink data notification. It will send it to the MME, and within this message, including some information related to the API, EPS peer identity. We'll show this in the next slide for the code flow using Wireshark. Then directly the MME will send the paging, right, for the each unit B within the tracking area update. Actually, this paging information, the paging information, this will be sent for each tracking area, for each unit B within the tracking area. For example, assume that you have one tracking area update and consists of 10 unit Bs. So the paging will be forwarded for all of them, and unit B will start forwarding this paging until the user using the rate. And we'll explain, find his paging, the user. Once the user finds his paging, he will reply, and this will now establish a connection between the serving gateway and the user. And now the buffer data can be forwarded, which is now having this signaling and media period being recovered. And now the serving gateway can forward the 7 byte. And after that, the EUE can continue with the process normally compared after the 7 byte. Once you receive, will just complete with the process. So now, next slide, we'll explain the details about the messages context and what kind of failure scenarios we might face in case of mobile terminating. So now let's move forward to see what we have. So this is actually the overall entities which we have it. Let me first explain to you. As you know, this is all the entities, UE, NOD, MME, and serving gateway, and sometimes we call it SPC. Actually, first of all, just let's recall what kind of interface is being used, or interface to connect between both of them. And then we have something called protocol. It's like let's say the language which is being used to communicate between these different entities. So we have RX and GX, RX between PCRF and CSF, proxy CSF, and GX between packet gateway and PCRF, and this is used diameter protocol. Then we have GTP V2. This is V2 usually used for the control plane, and this is the protocol used to communicate between packet gateway, serving gateway, and MME and serving gateway, and this is having interfaces. So now let's go through what we're expecting from the traces. So as you know, this is for the terminating call. So the proxy CSF first thing will receive the SIP invite, right, from originating. Once it receives the SIP invite here, it will just directly forward this SIP invite to the PCRF and packet gateway. So they will understand that there is now ongoing traffic, but they know that the user already in idle mode because there is no connection S1 and S11. This kind of interfaces or tunnels between both of them is being released, and even the radio bearer. So they won't like to activate this one. So what will happen? The packet gateway, it's know that there is data coming already from the SIP invite, and PCRF already notified through this SIP invite that there is a data already incoming for this particular user. So it will send this data to the serving gateway called downlink data, just notifying there is incoming data. So the thing that, as you mentioned in the previous slide, serving gateway will buffer this kind of data until it having the connection being established. But after that, the serving gateway will forward this downlink data, but it will just notify the MME that there is already ongoing data is coming, and within this downlink notification, we have something called EBI. And EBI, this is just telling them about the EBI or EBS peer identity, for example, identity 6, which means we'd like to establish now the PCI5 and the all related default peers as well. So this will notify about that part. Then The MME should reply with downlink data acknowledgement. Acknowledgement, not acknowledge, acknowledgement actually. Forget about this. Acknowledgement in case if the UE and the inode B processed the paging domain. This should not come after the inode B confirmed that user already replied. So once the MME received this downlink data notification, the MME will forward this paging message to the inode B. But just again to stress into this point, the MME actually initiate the paging procedures by sending paging message, okay, to each inode B that serve belonging to the tracking area, to the cells blocking the tracking area. For example, assume that you have 100 cells or 10 inode B as you mentioned before. So this paging message will be forwarded to all the inode Bs which is falling within the tracking area update, which within this paging information. This is we're showing now from the workshop. This is the information within the paging information. We have something called UI identity index. We have something called UI paging, which include the STM, the MMID, and we have the CN domain, whether it's CS or PS network, and for sure because it's VoLTE, so it's operating over PS, but in case of CS fallback, for example, it will operate over CS domain. Then we have the tracking area update list, and this is considering having the MCC and MC and BLMN and tracking area update. So it's know the tracking area update, so it forward the paging to all the InnoDs within this particular tracking area update. Then after that, the InnoD will process or will move or forward this paging to all the each InnoD will forward the paging for all UEs under that particular InnoD until the UE who having his, for example, it's usually the paging using this paging RNTI. Once the user detect the paging, will just start initiating now after something called ROHC connection. We'll show that part now shortly. So next step, actually, I would like to show you the context of each of this message from our chart. I will open it now, but before doing that, I would like just to explain quick information and very interesting information before jumping to the chart part. Actually, here I would like to explain some information which will be very important in your troubleshooting and even optimization if you're would like to do some optimization even from RAN side or the MME side to improve the paging in general, success rate or paging like the delay or latency or whatever. As you can see here, for example, in this figure, this is the MME. It's already forward the S1 AP paging, and once it's forward the paging to the inode B, the inode B now, the MME will start timer called T3413, and actually this is a supervision timer for the paging procedure, supervision process. And actually the MME can reattempt this paging process procedures in general if this timer expired before it's received any confirmation or before it's received this particular message from the UE, from the inode B. For example, if this process, if the user didn't receive the paging for some problems, for example, user is out of coverage or whatever, so within this particular time, if he didn't receive a reply or feedback from inode B, so this time will be expired, so it can again initiate a new paging. This is actually the main idea about that part. And actually, usually the implementation of this T3413 is you can say it's different from one vendor to another, but it's kind of similar. So this is the first thing. So I just again need to recall some important information about how the inode will know, for example, the information about this particular users and what is, for example, his frame number, what is his UI identity and so on. For example, if you remember here, we mentioned that we have UI identity index, right? This is actually used by the inode to calculate the paging frame, the PF, right? The paging frame. How doing that? Doing that through using a formula, which is this formula. Actually, it's will directly being sent to the user, directly being calculated already. And it's actually equal UEMZ, the MC mod 1024. So this is based on that part. The inode will understand what is the paging frame for this particular user. Then the UE paging will tell them this is the STMC for this particular user, and this is the MME ID for this particular user. And CN domain will just tell them this is the paging, and as we mentioned, the tracking area update already the inode will know the paging will be forwarded for each tracking area update. And once the paging is being sent to the UEs, there is a DRX cycle. For example, the user will wake up this paging occasion, right? Just to start decoding the PDCH. So this is also parameter. If you optimize it, for example, decrease the woke up scenarios, so you might get even better delay or even better success rate for the paging. So the user will not miss the paging is being sent from the inode B to the UE. So also this is another scenario. So what kind of failure scenarios you might see, right? And while implementing in case of the user in idle mode, it actually we can say it's classified into three scenarios, right? The first part that maybe this paging DRX cycle is very large, it might prevent some users from detecting the paging, even giving a delay or failures, or even the tracking area update itself is being defined wrongly. So if it's defined wrong with this InnoDB, so it will forward the paging to a wrong tracking area, so the user cannot receive, or for example, the user already out of coverage. So this is the three common scenarios which you might face it in general. But here, just to explain, once the user receives the paging, he will just start the random access process. Then he will start sending this RSU connection and initiate something called a service request, as mentioned here, which through initiating you initial message, and he will initiate this kind of service request, which is saying that this is bundle terminating. I would like to initiate now. I would like to start getting my context or the PCI file being established. So it will just sending this particular message. So now let me open the Wireshark to show you what kind of information we can see directly from Wireshark. And this is just will be something interesting in case if you're using Wireshark to know how to check. So now, as you can see, this is a Wireshark. As you can see here, this is a source and destination. Usually you'll find IP here, but you can convert it into, if you have the IPs, you can convert it into the entity or node name. So as you can see, the first message here is called downlink data notification, right? Which is this particular message being sent from serving gateway to the MME, as shown here. So this message, as we mentioned before, it should include the EBI, right? Which is called EBS Pure Identity. So let's explore and see what we have within this message. I'm just telling you only about the BCP identity. So let's view the packet details. Okay, as you can see here, within this packet details, as you can see here, we have the message type first, which is downlink data notification. And we have the tunnel endpoint for this particular message, which is being the tunnel endpoint for the MME itself. This is the tunnel endpoint. Then we have this EBS Pure identity, which is EBS Pure 6. And already the NOD know this is equivalent to which, for example, quality of service or which KSI. So if you right click here and you expand this subtrees for that part, you'll find just information of this EBS Pure down here. This is telling him this is my EBS Pure identity, and then it's showing some information about the allocation retention priority. So this is downlink notification. You can see now the InnoDB starts sending, the MME starts sending once received this downlink notification, the paging, and you'll see that paging is being repeated a lot. Why? Because as we mentioned, it will send the paging for each InnoDB within the tracking area updates. Assume you have 10 tracking area update, 10 InnoDB within the tracking area update, so it will send for all of them. So for all of them. So what kind of information you have here in the BIS paging? If you click this one, as we mentioned before here, you will find this S1 AP application protocol. And this one, it's telling them that this is, let me click here. This is actually the information which you have at this part. This is the paging. This is process. It's a procedure. It's procedure codes ID paging. Within the paging, we have this information which we already highlighted here. This is above here, as you can see. First one, UI identity index value, which just defining the frame number where the user would be served. Then U paging identity, which having the STMZ. If you open this part, for example, let's expand subtrees. It will having the STMZ and it will have the MME code as well. Then you will have the CN domain. If you export this part as well, you will have this one, for example, tell him this is a PS network, right? Because this is VoLTE. In case of CS fallback, it will be CS. Then the tracking area update list, it will having the tracking area update, PLMN, and MC and MCC. This is actually all the information which being mentioned here. So once the InnoDB found that this user replied, if you go down here, more, if you go down and down, yes, if you can, let's first hide this part, like the details. See now, downlink notification being acknowledgement. It's being replied here. This means that this paging, this message should come after the paging being received or responded. This means that the user already found replied, the user being replied, so downlink notification acknowledged, this message being sent. So after that part here, the user now should start initiating the call, which is, as you can see, if you go up here, you can see that the user now start initiating an initial message service request, say being sent from the InnoDB to MME, because from the user side there is ongoing ROHC connection and even the RATCH process, and this is he will send service request, and this service request it will be piggybacked, as we mentioned in the previous session, within the initial UE message, and this is will including a very important information which already explained in the previous session. So once as I mentioned, once the paging being received now, what will happen? Just exact the same as we explained in the previous session. You can refer to the previous session if you would like to get the details for all these messages already explained in the previous session for the mobile originating. these will be exactly the same. User just will be sending the ROHC connection process. It will send this initial UE message, which you just showed, including service request, and all this kind of information will continue same as we have mentioned before. And actually, that's it for today's session. I just would like to highlight one last part. I will just upload this documents or the documents after we finish all the training session. I will add it to the video description so you can get or use these documents for your reference. And here I just added one more slide I already explained in the previous related to the network initiated service request. And in general, service requests can be initiated even by the user or by the network. By the network in case of terminating calls, by the user instead of mobile originating call. And this is just the service request. Hello everyone. Welcome to the new session of the end-to-end VoLTE training campaign. In today's video, we're going to go through the VoLTE key actions, including the main features and also the parameters, which can be done to improve the VoLTE performance. We'll cover firstly the high-level view of the key features and actions which can be done in the network. Then we'll try to go through one by one, especially for the VoLTE features part, which is more related into RAN part. So let's move forward and see what we have. So actually this figure or mind map is summarizing like some of, or let's say the VoLTE main key actions. As you can see here, I split this one into 4 categories. In general, usually when you optimize VoLTE networks, you will just look into features or actions or features in general, which can improve coverage and robustness, okay? Then you have the mobility management, where you can improve, for example, the network performance through improving the layering strategy. And you have different features. Then we have some specific parameter tunings, including whatever mentioned here, as for example, tuning the maximum HARC retransmission. Then you have some actions which is more related into end-to-end view, which can improve the VoLTE call setup time delay. So our main focus actually would be in the first area, which is related to the main features in the VoLTE. So in today's video, we're going to cover the first 2 parts, which is related to TTI bundling and robust header compression. And the main important point that I will be covering those 2 parts also from using the logs, just to show you how to verify the feature functionality and how this kind of feature you can confirm how this kind of feature is working from the logs or not. So let's move forward and see what we have. Actually, before I jump into the details of the 2 main features which we are going to cover today, I just would like to let you understand. Usually, any feature tuning will rely or would depend on this kind of box, which is related to the what kind of inputs is being reported to the ENOD and or being configured within the ENOD and or the BTS, and what the ENOD do and what kind of resource will be allocated. So if you look into this box, you'll find that you have different inputs. I'll just give some of them here, which is, for example, UE-related inputs related to the UE capability, measurement gaps, and the synchronization stats, and so on. Then you have this kind of HARC feedback, which is, for example, the user replying for its acknowledgement or non-acknowledgement, and this can have some configuration from the ENOD, for example, to increase the number of non-acknowledgement trial or retransmission trial, which can be done from either in downlink or uplink. Same, you have the ENOD will differentiate between the surfaces, for example, using the XCI. For example, XCI1 will have a different budget delay or bucket budget delay compared to, for example, XCI9 or 5 or 8 or even 5. So as overall quality of service parameters, not only for the packet delay, I mean. And also you have this kind of channel input CSI, which is being reported just to indicate to ENOD what kind of radio condition of these users is being now, for example, what is the CQI channel quality indicator and so on. So the ENOD can start selecting his MCS selection and so on. And you have also the downlink power configuration. For example, you can have the reference signal power, you can increase it, decrease it. You can have some optimization in BDCH power, you can increase and reduce it. Then you have the transmission mode, whether you are going to use closed loop, open loop, and so on. All these kind of inputs, the ENOD will take these inputs and we'll try to make the calculation for the scheduling calculations and to check what kind of priority, for example, which users having highest priority for in terms of scheduling compared to the others, start to, based on these inputs, selecting the MCH and so on. Then it will decide which user is being selected for the scheduling and the resource blocks, for example, which being allocated for user and MCS. Why I'm using this part? Usually any features or even parameters or even any optimization actions, if you understand this box very well, you will be able to know what you can do. For example, if you would like to increase the robustness you can increase, for example, the number of hard retransmission. But still, this is, you need to understand that this, for example, can increase retransmission resources. So you need to be very careful whenever you optimize this kind of things. But any action can be done here. It can having improvement or even degradation on your inputs. So just like, you need to understand that in general, VoLTE is, or even 4G or 5G, is more about link adaptation, how the unit is doing link adaptation based on the inputs you are giving or even configuration. So again, all the feature will be playing in this inputs here in order to optimize and get a good results as a scheduling results for the user. So let's move forward and see what we have for the two features. So the first feature we're going to cover is related to TTI bundling. As you know, this TTI bundling is, you can say it's now becomes like standard features, as it's almost enabled by default for any vendor or even operator, and it's like mandatory, one of the mandatory features that must be enabled. But in today's session, I'm try to cover it from different perspective. Also, I would like to add one additional point related to something called advanced TTI bundling, which is need some optimization, sometimes need some to be enabled for some vendors and so on. And also you need just to understand how this kind of advanced TTI bundle is working. So initially let me explain how TTI bundling in general is working. In the normal case scenario, if you look into that part here in the left, in the normal scheduling scenario, the resources will be scheduled right in 1 millisecond. So all the data will be sent, for example, within particular TTI from the unit B, the UE in terms of uplink to the unit B will be transmitted in this particular TTI. But once the unit B trigger TTI bundling, and in general how TTI bundling is being triggered, TTI bundling actually is being based on uplink SNR, PUSCH SNR. So for example, if this uplink SNR is falling below a certain configured threshold, let's assume that the threshold of the SNR is 10 dB, and now the user is having 7 or 6 dB or whatever. So the unit B will decide that this user should enter the TTI bundling state because it will assume that this user having a bad radio condition. So the NDB would like the users to enter the TTI bundling state in order to get a better performance in terms of uplink. How this can be done? The NDB will send RRC configuration message to the user, asking him, now you are in TTI bundling state, so now you can start using the scheduling of the TTI bundling. So in general, how the scheduling of TTI bundling is being done, as you can see in the figure, assuming now that before the normal scheduling, the user was transmitting one, for example, transport block here. Now this one will be retransmitted or being sent by the users. Like the same data will be sent 4 times in 4 consecutive TTIs as shown here, but with different redundancy version. But the same data will be transmitted. Accordingly, this will be reflecting in the decoding process from the unit B side. This will be like a diversity, so that you will have higher energy per bit. So that this means you are improving your uplink coverage because you have a better decoding from the unit B side because you are sending 4 different data and 4 consecutive TTIs. Sorry, same data in 4 consecutive TTIs with different redundancy version. So this will improve the redundancy performance and will result in higher energy per bit. So this can improve the uplink coverage by around 2 to 3 dB. Now the idea here, as you can see for the acknowledgement part, it will be sent after 4 milliseconds from the last transport block with being set. For example, here you need to count 1, 2, 3, 4. So this will be like, you assume from the first packet till the last, it should be around 8 milliseconds. While in the normal scheduling, it will be sent here for the acknowledgement. So this can be, you can assume it as one of, it can increase the delay a little bit, but usually the TTI bundling is more triggered for the very bad users, especially or edge users for the uplink. So this will have a good performance. The second and the most important part as well, now explain that in terms of coverage, you will have a higher energy per bit, so it will improve your uplink path loss uplink coverage by around 2 to 3 dB, sometimes up to 4 dB. But still, you have also some capacity gain. How this kind of capacity gain you can observe this capacity gain based on TTI bundling. In case of without TTI bundling, if the user is already in the edge coverage and he having a very poor performance on the uplink, so in this case, he will need to have this kind of RLC segmentation. He is having he have less energy now or have less power because he cannot send the complete packet in one time because he have limited uplink coverage. So the user will the RLC layer will do the segmentation into, for example, as you can see here, four buckets. For example, instead of 1, it will be sent in 4. And the idea that, and it will be sent in 4, as you can see, in 4 transport block, each one will be sent in different TTI, but this different data is being split. Why here the splitting is being done? The splitting is being done to increase the power per bit or per resource block. So you will have a much better coverage whenever you do a segmentation. But also the segmentation is increasing or decreasing the capacity, because for each one of those you will require a BDCH allocation, right? Then it be which TTI or which he can send this particular data. So you need a 4 BDCH allocations, and also for each one of those you will write the your UE will require to send acknowledgement for each of those packets which being sent in the TTI. So this is also increasing the hard feedback. Instead of one hard feedback, you have hard feedback. But in case if the TTI bundle is being triggered and the input be already instructed the UE to enter the TTI bundling state, what will happen? In this case, the user know that there is a better performance or better decoding and even having higher energy per bit. So because he's in TTI bundle state, so he will send a complete RLC. For example, it was SDU, BDU. It will send the same one without any segmentation. So this will result again in sending this same TB, but only transport block and for TTIs. So this one would result in less BDCH allocation. So it can have improvement in your BDCH allocation in case of the segmentation point of view, and also will have one hard feedback, because for those four TTI, for those four transmitted data, then same data in 4 consecutive TTI, it only require one hard feedback. So in this case, you will have a better performance in terms of improving capacity, because you will not have any RLC segmentation anymore. And also one of the things that can be triggered out of the TTI bundling, whenever the users enter the TTI bundling state, he will be out of the DRX. He will exit DRX directly, so he will not be in DRX anymore. So this also can have some reflection even in latency or even in the quality point of view. So this is the 3 main gain of the TTI bundling. And just a side note, usually the TTI bundling is supported by FDD. It can be supported by TDD in very specific cases and depend on the, as mentioned here in below comment, depend on the subframe configuration. Usually we use this subconfiguration 2, which is SA2, which is called subframe assignment, which is as a location, it's 622, means 6 for downlink, 2 for uplink, and 2 for uplink. 6 for downlink and 2 for uplink. And 2 can be guard band or can be like having a dynamic between uplink and downlink. And the idea that usually that the TTI bundling require 4 TTIs for uplink, right? That's why you will have a limitation TTI bundling. That's why it's only being supported by this kind of configuration, 0, 1, and 6. But usually those kind of configuration is not being used. Usually use the subframe configuration 2. And also doesn't work with the semi-persistent scheduling for the same U. So this is just an extra comment. Now let's move forward to see how can you verify the TTI bundling from the UE logs. And secondly, what it means by advanced TTI bundling. Before going to the advanced TTI bundling or how to verify in general TTI bundling from the DT logs, I would like to just recall one point. One of the limitations of the TTI bundling, once the TTI bundling state is being triggered, you will see if you read this, if you quoted this from 3GPP, we can see that if the parameter of TTI bundling provided by high layers is set to true, means TTI bundling is being triggered, then the modulation order, MCS, will be set to 2, and this will be like QBSK, which means you have only 2 bits can be transmitted in the uplink, and the resource blocks will be limited to maximum 3 resource blocks. So in this case, what it means, but once the bundling is being triggered, so assume that the user is doing a VoLTE call and he have uplink data or you need to do something on the uplink, so your uplink data will be very limited in this case of the TTI bundling. So this was using the TTI bundling, this was causing a limitation uplink through. But after the release, starting from release 12 upwards, the 3GPP like introduced this capability for the devices, which is if the user is the user to release 12 and he will be supporting this like in the capability, you can check this kind of information, which is called no resource restriction for TTI bundling release 12. This means that you support TTI bundling relation without resource allocation restriction. This kind of resource blocks will not be any more applicable for those release 12 users. And usually we call this as advanced TTI bundling. And also there is one additional functionality which can be done. Here is called enhanced HARC pattern FDD release 12. This means that here for the you support something called enhanced HARC pattern for TTI bundling operation for FDD. Usually that in case of retransmission, in the normal TTI bundle, it requires 16 milliseconds for the normal users to make the retransmission. But in case of the enhanced HARC, it will only require 12 milliseconds. So this can be reflected also in latency improvement. And I will show you an example from the logs how to verify and how to check this kind of capability, and how to check whether advanced or enhanced HARC is being enabled or not. So let's see. So here we'll just check how advanced TTI bundling or TTI bundling general is to confirm from logs whether it's being activated or not. And the second point that will explain what it means by enhanced HARC pattern release, and we'll check also how to confirm the logs. The first two comments here is just quoted from 3GPP document, which I just showed to you in the previous slide. So initially what will happen, if the first of all, the E2E will check whether the user is achieving the TTI bundling condition, which is again based on the user's uplink radio condition, which is SINR. So assume that he's not achieving, so he will not be triggered. So the E2E will decide that this user is not a candidate for TTI bundling, so no TTI bundling will be triggered. But in case of the TTI bundling is being triggered, then the E2E will check the capability of this user, whether he's supporting this enhanced HARC pattern release 12 or not. If it's not supporting, then the users will use the old process, which is read to the binary release. So the HARC RTT is 60 milliseconds, as I mentioned, and the maximum uplink BRBs will be limited to 3. So those particular users, and even if the feature is not being enabled, will having a limitation in even uplink, and will having kind of latency increase. So this is kind of the drawback. But in case if the capability is being supported and this feature is, or this parameter is being enabled, and this is, you need to check with your vendor, maybe they have a different perspective, but this is just from 3GPP. If it's being enabled, so that the bundling, this means the bundling release 12 is being supported, so the HARC RTT will reduce from 16 to 12 milliseconds, and now you can get even more than 3 resource blocks for the uplink allocation. And in the right figure, this is how to confirm in general how TTI bundling is, whether TTI is being triggered or not. First thing you need to check under the ROHC configuration message will be sent from the E2E to the UE. Under this ROHC configuration message, you will find something called radio resource configuration dedicated, as shown here. Under that, you need to check the MAC parameters, which is MAC main configuration. You'll find if it's being triggered, this one will be true. If TTI bundling in general is not being triggered, this one will be false. This is for the normal HARC. But in case of enhanced HARC, as you can see here, also it will be the same. If the user supporting is fine after MAC, under MAC configuration V1020, we'll find that there is additional something called HARC pattern release 12 is being supported, and this is indicate that the user now is falling under this category, so he even can have a better latency and has no limitation anymore in the uplink resource block allocation. So this can also give a better performance in terms of uplink through. And this is all what I need to discuss about TTI. Now let's move forward for the second feature, which is robust header compression. Okay, now it's about robust header compression. This is also a standard feature which is usually enabled by default. You just need to check or make an audit for your network, but usually this is being enabled. But let's just explain how this feature is working and what kind of improvement we can get whenever we enable this feature, and how also to verify from the draft test whether the feature is being enabled or supported by the users or not. Okay, as if you can recall, robust header compression in general, what it do, as mentioned by the name, as stated by the name, it just make a header compression. So the main advantage of this feature is trying to reduce or make a header compression to reduce in general the packet size. And if you reduce the packet size, you will be able even to improve your uplink performance or block error rate, because you will have, for example, assume you're using 20 resource blocks on uplink allocation, but after the packet reduction, size reduction, you need also to only to use 10 resource blocks instead of 20. So you will have even more power per resource element. So this will be reflected in you having a better uplink coverage and even less block error rate, or much better block error rate. So the main advantage here, you are improving the capacity in general because you are doing a reduction for the packet size, and you're improving your uplink performance, especially for block error rate and coverage as well. So this is actually the general idea in the left here. If you look into the left as a general high level concept, you see, for example, this is the compressor and this is the decompressor, even sender or receiver. So in the compressor, what's happening in the first, when the packet is being transmitted, as you can see, you have the data or the payload, and you have some here additional header, which is IP header, UDP header, and RTP header. And usually the IP header is having very high size. So actually, the main idea that I would like to confirm that this is happening at the BDCB layer. This is the robust header compression is happening at the BDCB layer. So at the BDCB layer, you will be having a compressor. The compressor will establish the context. I will explain this one in more details. Then it will be transmitted. The compressor and the compressor will have an establishment of the context through sending the first packet in general as it is, without any compression. The first packet will be sent from the compressor to the decompressor or sender to receiver. Without the first packet will send without any compressor, but both of them will establish a context out of this packet. For example, this packet have a specific sequence. If you can see here, this packet, for example, is 21XX01. So we found that there is some static numbers within the packets. This is all the packets. It's 21XX01, 21XX02, and till 06. And that the compressor will understand that the context of this one is 21XX0. So they will establish the context, which is, as you can see, between the compressor and the compressor. The first one will be sent as it is. Then they will establish the context, which is 21X00, as highlighted here. Once the context is being established, now only the one which is out of the context will be transferred. So before you used to transfer, let's assume this one as 6 bits or 6 bytes, for example, 1, 2, 3, 4, 5, 5, 6. Now we need only the compressor need only to pass only one packet, and the decompressor, because it's having the context being established, can decode the data successfully. So in this case, usually instead of, or initially you would like to send, for example, 6, let's say bytes, multiply by 6 also, which is 6 numbers here, you will have 36. So once you establish the context, you need only to transmit 11. 11, why it's 11? Because the first one you need to transmit as it is, which is related to 6, then 7, which is the last digit, 8, 9, 10, 11. So you have 11. Then you need just the compression ratio will be around 70%, because usually you need to transmit 36, but in this case you are transmitting only 11 instead of 36. You have around 70% improvement or reduction in the packet size, and this is how it's been working. And as you can see here, usually this is what happens after the header compression. For example, here you have the larger size of the header is related to IB version 4 or IB version 6. IB version 6 even having higher packets. So usually the robust header compression will reduce it to around 1 to 3 bytes. And if I can recall it, usually IB version 4 have around 40 bytes as a size, and IB version 6 will have around 60 bytes. So at the end, it will reduce to only 1 or 3 bytes, and this is how we get the gain. So now let's jump into how to verify first the capability of the device from the logs, and what kind of requirements, which parameters we need to check from the logs, from the capability, and how also to confirm whether it's being triggered by the E2E or not. Okay, if you look into this figure, this is actually the figure on the left here. This is if you look into that part under the UE capability information message, which is sent by the UE to the E2E. The UE is informing the E2E about its own capability. So you need to go through under the BDCB parameters. As you mentioned, that ROC or ROHC is supported by the BDCB layer. So the user is sending something called profile 1, 2, 3, 4, 6, and so on. Actually, usually the voice or the robust header compression for the voice is about profile 1 and 2 and even 3, but those or especially 1 and 2. So you need just to check whether those being supported or not. If it's false, this means this particular user is not supporting the robust header compression, because you need support profile 1, 2, and 3 as shown here. So this is the most important from the capability point of view. So you might do some insights in the network to check, for example, how many users supporting the feature or not. Then we can, for example, raise it to the vendors to try to ask them if some device is not supporting, to ask them to try to add the capability for the devices. And here from the E2E side, whether during the RSC configuration when sending KSI1, RSC configuration to configure KSI1 data radio bearer, it will send under BDCB configuration data, again ROHC in the BDCB layer. So if it's sent not used, this means header compression is not being activated. The feature may be off, not be working. So this means it's not being or even the user not supporting. But if it's being activated, as you can see here, it will send under the same part here, BDCB layer, under the BDCB configuration. Here, for example, first the RLC, as you know that for KSI1, it's usually using unacknowledged mode. And here this is the ROC configuration. So it will send profile 1 and profile 2, which is showing as true here, which is indicating that yes, robust header compression is being supported. So now we can start establishing our context. So the first feature we're going to cover today is called XDRX based on SNR. This can have a different naming for the vendors, but in general, this is a very simple feature and having a very simple mechanism where the input B will simply instruct the UE to go out of their to completely disable the DRX for this particular users, for a specific users, in case if the user's radio condition in the uplink is falling below a certain threshold. So what kind I mentioned here based on SNR. For example, let's assume that you have a configured value for uplink SNR in the InnoDB side. So you configure this value for 5 dB. So the InnoDB all the time is measuring the uplink radio condition of the users, either based on the SRS, if it's being enabled for FDD as an example, or which stands for sounding reference signal, or for example, measuring in general, estimating the uplink BUCHF SINR. So in case if the SRS is not being enabled, so the InnoDB will estimate the SNR, and once, for example, it's found it's falling below the configured threshold, which we assumed as 5 dB. Let's assume now the user is having 3 dB or 2 dB SNR. So the InnoDB will send him a RSU configuration message to disable completely the DRX to ensure that this user will never enter the DRX whenever his uplink SNR is in a poor radio condition. So what is the benefit we can obtain for that part? Actually, as mentioned here, the three main benefits where we can obtain from disabling the DRX in general, which is reducing the packet loss. I will explain why and how, and also improving the voice quality and downlink scheduling delay. So now, just to understand from where these gains might come, let's try to recall our understanding of the VoLTE DRX or DRX in general, particularly for VoLTE. So before explaining the concept of this kind of improvement, where it comes, why it's coming when we disable the DRX, just let's recall three main important parts. The first part, in 4G retransmission, usually if the user is out of TTI bundling state, is remaking the retransmitting every 8 milliseconds. Means that if the users fail to decode there is a failure to decode, for example, the packet, transmitted packet from the InnoDB side, the retransmission will happen after 8 milliseconds. And the second one here, which is the VoLTE packet delay budget, as we explained in the first session, it's 100 milliseconds. So whenever the packet is delayed for a value greater than this 100 milliseconds, this means the packet will be discarded. It will be even lost or discarded. And the second part here in between, that we mentioned that the InnoDB usually will buffer the data in case will buffer the data in the buffer. It will keep it in the buffer in case if the user is already in DRX mode. So it cannot send the data to the user until he is out of the DRX mode. DRX means discontinuous reception, where the user is in sleeping mode, so he cannot receive any data. So let's now try to explain what we have. Now, as you can see here, this is the settings where we assume there's something called end duration parameter for DRX. It's 4 milliseconds. We'll explain what it means by this. And long DRX cycle, which is 400 milliseconds. And this is usually the recommended settings by Apple. As this is known, you can find this in most of the VoLTE networks, this kind of configured value. And for example, now let's try to explain through this particular mechanism. As you can see here, for this, assuming that now the InnoDB already received VoLTE packets and it would like to transmit these VoLTE packets and the downlink to the users. So this is the user, and this is the DRX state. So this packet cannot be transmitted from the InnoDB to the UE until the user go to the on duration timer. On duration means he's awake. He's out of the DRX and he's awake. He can now receive the packet. So in this particular case, the InnoDB can transmit it here. But if you remember that the VoLTE packet in general is transmitted every 20 milliseconds, as mentioned here. But in this case, because the long DRX cycle is 40 milliseconds, this means the packets will be transmitted every 40 milliseconds, but it will be bundled every 40 milliseconds. We'll have 2 packets. So now the InnoDB will buffer the packets until the user go to the on duration timer. As you can see, this on duration timer, which is 4 milliseconds. So the user is awake for 4 milliseconds only and is waiting for the InnoDB to start transmitting data. So the InnoDB now did that downlink transmission. As you can see here, this is the BDCH and this is the allocated, for example, packets and BDCH resources in general. So in case if this particular packet is being failed, it's not somehow it's not being decoded, or there is, so the InnoDB need to make the retransmission after 8 milliseconds, right? But this cannot be done, right? Because first of all, we have something again called long DRX cycle, and this long DRX cycle where the user will go into the sleeping mode. It's 400 milliseconds. So he will be awaking within this long direct in the beginning of long direct cycle for only 4 milliseconds, and the remaining 36 milliseconds would be in a sleeping mode, which is this part. This is the sleeping mode, and this is now awake mode. So he will be again going sleep mode, and the NLP cannot do the retransmission until the user again is in the on duration timer. So at the end of the long direct cycle, it will start a new long direct cycle, and the user now will come again into in the awake mode and duration timer here for 4 milliseconds and start receiving. Now assume that again this particular packet is being failed. What will happen in this case? It happened that now it's almost 80 milliseconds, right? So now they need to retransmit the same packets, but again after this long direct cycle, which is again after 40 milliseconds. And again, if you remember, we mentioned that the packet delay budget is 1 millisecond. So assume that the retransmission happened at the second 110 millisecond. This means it's crossing the 100 millisecond, so the packet will be lost and discarded. So the user will lose the packet. So actually, once you disable the DRX, what will happen? The NLP will have now will have the capability and will transmit the data or the packet at any time to the user, which means every 20 milliseconds it can be transmitted. So you will have many opportunities to retransmit the packets in case of the retransmission. In case of 2 or 3 retransmission attempt for this 40 millisecond, now we can have even having up to, for example, 5 or even more, because the NLP can retransmit the packets now every 20 millisecond, not every 40 millisecond, as an example for that part. Also, in general, as you can see here, that the transmission in general is sending every 40 millisecond, but in case if the race is off, so it will be every 20 milliseconds. So this also can improve the downlink scheduling delay or latency, because now the NLP, the users in DRX can transmit all the time every 20 milliseconds. And in general, the voice quality can improve if the user is out of DRX, because the latency is improving, so this can even having a better voice quality. So this is the main actually advantage of these features. And the last part I would like to highlight, it's about the trade-off. For sure, if you disable the DRX, this kind of long DRX cycle is just made to keep the users in the sleeping mode where there is no retransmission or receiving, so this can save some battery. And also there is some probabilities in case if the user in a very bad radio condition, he will not be able to receive this ROHC recuperation sent by the NLP, and this can result in even ROHC establishment, can result in cold drop. So this is like cannot be a trade-off of that part. And in general, the DRX settings can be checked from during the QCI1 setup. You will find ROHC recuperation message, including this on duration timer. For example, here mentioned subframe 4 means 4 subframe, which is equivalent. Each subframe is 1 millisecond, equivalent 4 millisecond. And you have the long DRX start offset, which is here mentioned as SF40, and this is equivalent to 40 milliseconds. And that's all about this feature. The next part I was just showing that this kind of improvement was observed after tuning this feature. The VoLTE uplink packet bad voice quality ratio from the OSS KPI is improved. As you can see here, the ratio was around 1.5%. It reduced to 1.1, even less. And for sure, the users in DRX, for example, before the user was entering more frequently, more users will enter DRX. Now less users are entering because now the users exiting the DRX. So this can be the impact from the KPI's point of view. Now let's move to the next feature. Okay, this feature actually, it's one of the very important features in VoLTE, especially to improve the coverage, which is actually, as mentioned by the name here, VoLTE rate recommendation. The 3GPP name is called Access Network Bit Rate Change. Simply, this is as a simple algorithm. What should be done? Initially, let's just explain what happens about this codec rate. As you know, I explained the codec rate in previous sessions. And the codec rate, this is, for example, assume that we are having a codec rate AVS is being used, or even wideband MR. So I assume that now during the calls, usually the codec rate is being negotiated during the VoLTE call setup. And during the call setup, the mobile originating call will be sending the same invite, his capability about the codec rate. Then the mobile terminating will be replying with his own capability ranges. Then they will agree and probably select the highest codec rate supported between both of them. But the codec rate will almost remain the same all over the call. Like this is the situation. Sometimes it will be changed, but actually I didn't see that much. But this is mainly about the device's decision to change or ask to change the codec rate type. But let's take into that. It's just being negotiated during the call setup, and it will be fixed almost all over the call. So assume now the users initially during the call setup started with EVS 24.4, which is the highest codec rate we can be used. So in this case, the users now start moving to a bad ready condition. Still, he's using the same codec rate, which is very high codec rate, sending was high bit rate and high samples. So in this case, the user is going to bad ready condition, but still using high codec rate. So this can observe into packet loss or even can drop a call. And now the user again moves to more bad ready condition to the very edge. Still, the codec rate is same. So actually, this feature is supposed to do that. It's supposed to change. The ENOD is supposed to work with the user to adapt or to make a dynamic change for the codec rate in general based on the vendor specification. For example, let's assume uplink, like if you are speaking about the uplink codec rate, throughput, for example, or SNR or whatever. This is based on the vendor specification, but in general, let's assume in one word, based on radio condition. So if the radio condition is going bad, the ENOD will instruct the users to change, or will instruct the user to change his codec rate. So this is the main, actually the main function of this feature. So this is what will happen here, that for example, if the ENOD found that the user is moving to bad radio condition, it will send them a new codec rate, recommended codec rate, and the user will start negotiating with the terminating one or bearing user to confirm that this is the new agreed codec rate, which shall be used by both originating and terminating. Both of them should use the same codec rate. But there is one very important point. This feature requires a UE capability. Usually, if you look into the current situation in the market, not too many devices supporting the feature. It's very old feature, by the way. Not many devices are being supported the feature, but expecting in the future that the devices will start supporting this feature, because it will be very important, especially with the voice over NAT deployment and even the 3G shutdown and so on. So these two parameters you're supposed to find or verify from the UE capability information message, which is being sent from the user to the ENOD, that this is supposed to be found, which is called recommended bitrate release 14 and recommended bitrate query release 14 as well. So this is supposed to be supported by the users in order to support the feature. Now let me explain some concept behind the 3GPP about this feature, which is very important. But just in summary, to summarize that feature, this feature actually will simply switch the code rate at a particular radio condition, which is actually can extend the VoLTE coverage. This is the main advantage. And also, it's not only decreasing the codec rate, it's the opposite way around. Assume the user moved from bad radio condition to good radio condition, it can even increase the codec rate, and in this case, can improve even the voice quality, right? So this is actually, it's working even decreasing or increasing. Decreasing means you are extending the coverage, giving a bit much better coverage, less packet loss, better integrity. And if you are increasing the codec rate, you are getting better voice quality. Now let's move to just clear some concept from the 3GPP. As you can see here, this is an example in case if the access network bit rate change, the feature is going to decrease the rate. This figure actually I quoted from the 3GPP, and this feature is supposed to be supported by both voice and video in general. So actually here, as you can see here in the third line here, which is step number 3, already there is ongoing RTB and the uplink from user 1 to user 2, and the media flow is UE, and this is a specific codec rate. Assume this codec rate is, for example, R0 centric. So now the access network, which is the ENOD, decided to change the bit rate for this particular user 1, because he found that, for example, he's now in a bad radio condition, so it will required to send him. So it will send him this uplink, which is ANBR, access network bit rate change net. It's found that the R1, that it would like to reduce the R1 because R0 is, in general, the codec rate now is the user in bad radio condition, so it will try to change the codec rate. So actually, this is required to decrease the codec rate, which is R1. This is decreasing the codec rate. So directly, now there will be a UE end-to-end decision. It will negotiate with the user N2, and it will directly send as long as it's decreasing, it will directly send the new packet with the decreased codec rate. As you can see here, UE start sending up the packet as the new assigned codec rate, which is less. Actually, the user will check the recommended rate sent by this ENOD, and it will translate it into codec rate, because at the end the codec rate is being controlled by the UE, and it will start transmitting the data and uplink to the other users using the new codec rate. And as mentioned here by the 3GPP, that in case on adaptation in general, the adaptation results in a reduction of the media sender bit rate, that it decided the aim would be to reduce the bit rate. So the change would be initiated immediately without any further signaling, which means, as you can see here, the UE once received the request, it will directly send to the other user with the new assigned codec rate, which is a less codec rate compared to the previous one. But in case if opposite way around, it's required to increase the codec rate, there might be some additional signaling. Let's explain that part. As you can see here, for example, for this one, access network bit rate change in case of MBR increase. This is the same concept here. The user will being like transmitting, and this is I'm speaking about the uplink packet now, not downlink. Just giving example for the uplink codec rate change. And so now again it was being transmitted. So the NLP now decided again to increase this time the codec rate, not to decrease it, to increase the codec rate. And in this case, because it's increasing codec rate, actually the normal case scenario and some the depend it can be directly happen to increase the codec rate, because at the end the user one know what is the maximum supported codec rate by user two. But in some particular scenarios, if this other user, which is user two, for example, and this user believes that the most recently received MBR, which is a new ANBR being sent for its uplink, no longer applies, or it's not cannot be accommodated by this particular users, it will send something called ANBR queue, which stands for Access Network Bitrate Change Query, to requesting the NLP to check his radio condition, for example, and start assigning another bitrate instead of the one being sent by user one. So, and this is for sure require the capability by both device, require this particular devices in case if it's being supported the capability of this ANBR queue, which is stand for query. So in this case, only if it's being supported by user two, it will be requesting the access network to charge the change. And the NLP now will assign this new codec rate. For example, assume that now this is R3 and this was R2. So now the user will send, so from user 2 will send to user 1. I would like to, this is to receive at this particular codec rate, and then UE1 will be start transmitting with agreed codec rate between both of them, and the media will be start set up with this additional signal, which is the codec rate being sent by the user 2. But this is just in case the user 2 is not being supported, if being supported the feature in general, and also in case if both nodes AN1 and AN2 is supporting the feature and the feature is being enabled. And the normal code scenario, as I know, that it depends on the vendor specification. This can be done directly, because at the end the codec rate change is being always negotiated by user 1 and user 2. So this even is this particular step where there is a query from the user 2 to the access network or NLP2 might not be done. This is actually 3GPP explanation, but you might find some differences compared to the vendors. But in general, this feature doesn't require any support from the core. It's mainly about that device capability. So you can have a try and check what kind of impact you can see in case of the codec rate, for example, change, how much the coverage is going to be extended and so on. So this is from the theoretical point of view. Let's move now to the last feature. Actually, this is the last feature, which is actually about downlink, uplink frequency selective. If you're already working with a 4G network since long time back, even this is very well known feature. It's not only for the VoLTE, it's even for the PS. And it's very simple features where, as you can see from the figure here, assuming now we are speaking about the uplink frequency selective, from the name it's being kind of obvious that in the normal case scenario, as you can see from the bottom down here, that without the feature in general, the resource allocation, which is resource blocks, will be happening in a sequential manner. Assume that user 1 required, for example, 4, 3 RB, 10 RB, whatever. So then B will start assigning in a sequential manner. Once it's assigning here, it will now start assigning for the user 2. It's not taking the radio condition of this particular frequencies into consideration. But in case of frequency selective being enabled for the feature, even for uplink and downlink, so the NLP now will start measuring, for example, if you're speaking the uplink, it will start measuring the uplink quality, and it will start estimating. It will start estimating the quality of this user. And this part, it's about the uplink SRS or uplink PUSCH SINR. I think I by mistake I mentioned the first feature, which is the XDRX based on SNR or SRS. The XDRX is only based on the SNR,
but this feature can be being based on SRS, standing reference signal, if it's being enabled, or based on the SINR. This is how the ENB will estimate whether the user is having a bad radio condition in this particular RB zone. So assume now you have this user one here, UE1. This is the channel quality. So in this particular frequency, area is getting a good quality, so it will be assigning this as this way. For example, to give him this particular portion of frequency, assume that the frequency is at the start of the band as an example, it will assigning him. Now the user 2, now as you can see, this user U2 allocation, this is the frequency domain. It's starting assigning, for example, this particular area because it's having good quality. User 2, it's assigning him this particular frequency, which is here, for an example, at the end of the band or mid of the band, because here user 2 quality profile is getting better. So now it's being assigning not in sequential manner anymore. It can be at any part of the frequency domain as showing here. So for example, instead of being in sequential manner, now it can be done in this way, where, for example, user 1 taking the resources here, and user 2 not necessary to be continuous allocation, as you can see here, between user 1 and user 2. It will be starting at the end of the band, and this can guarantee that you will have a much better quality and even much better voice quality and even much better packet loss. This is actually the main idea, and this is I think it's very simple feature and it's well known. And if you are speaking about downlink frequency selective, this is usually based on the reported channel quality indicator, which is CQI, which is usually reported from the UE to the InnoD, and the InnoD based on the CQI can start doing this same concept, where it start allocating the good resource blocks for this particular users, instead of allocating a particular or in a particular way, as mentioned before here, without frequency selective. The first feature we're going to cover today is called PUSCH uplink resource block reservation. This can have a different naming between one vendor to another, but the idea of this feature is very simple. The idea of this feature that you can reserve a particular PUSCH resources to be used only by VoLTE users. It will be only reserved for VoLTE users and it will be only used by them. So what is the gain of such? What kind of gain expected and what kind of drawbacks? So if you look into the figure below here, this is like the different cells, and this was the uplink interference for the resource blocks, allocated resource blocks. If you look into this particular area, the red one, you can see that there is high uplink interference at those particular resource blocks here. So if the VoLTE users being occupied those particular resources, this might cause a voice quality issues and might impact your MOS, right, and voice quality in general. So VoLTE is more sensitive to the interference compared to the data. So this feature you can look into, for example, the allocated resource blocks for those particular cells, and you can, for example, you see this area is the best area. You can reserve, for example, 3 resource blocks to be used only by VoLTE users. And once those resource block is being exhausted or occupied, still the VoLTE users can use the remaining resource blocks, but at least you would ensure that as a start point, they will be using the clean band or clean resources. And those resources also will never be used by data. So this resource will all the time being clean, because there will be no any transmission from data users across the same resource blocks. And the drawbacks of that part, for sure, that as long as you're reserving those for VoLTE users only, so this might impact your peak throughput in general for the uplink, because this will be all the time reserved for VoLTE users and cannot be used by data users. So the main recommendation usually for such features to be used as a scenario based. For example, to use it for a particular cells where you have high uplink interference and you would like to reserve a particular resources for those users. Also, there is another scenario where you have huge congestion, for example, in the cells, and you don't like to impact the VoLTE users, so you reserve some resources for them. This is just scenarios. So usually this is like a scenario based. It's not being recommended to be done in complete network as an example. As you can see here, there is a clear gain in packet loss and block error rate once there was some resource being reserved for VoLTE. Also, the voice quality has been improved, as you can see here. So this is very simple feature, and the name of the feature can be different from one vendor to another. So let's move to the next feature. The next one, actually, it's also very simple. It's it's mainly as written from the name here. You can see it's called disable carrier aggregation for VoLTE users. For example, if you already have 4G carrier aggregation being operating, so you still can have VoLTE in the same time. So the VoLTE during the call, you can have a carrier aggregation. So why usually the operator recommend, or in general it's being recommended to disable carrier aggregation? Actually, this is because during the carrier aggregation, you can have some impact which might impact your call drop rate, especially for VoLTE. As you know that first all the carrier aggregation in general, it require the ENOD require all the time to deliver the A1, A2, A6 reports which related to the carrier aggregation, addition and removal, and carrier aggregation cell change, for example, secondary cell change. So for example, those required to be delivered by the ENOD. So if you have more carriers, you require more RRC configuration. So this kind of repetition or repetitive RRC configuration, this is might lead into sometimes into RRC reestablishment if the user is in a poor radio condition, in case if the user didn't receive the RRC configuration message. Also, in general, if you have multiple carrier aggregation, let's assume 2 or 3 carrier aggregation or 4, you require a repetitive SSL configuration, right? Even addition or removal. So this is also can have the same situation where the users during the call trying to add a secondary cell or third cell, or trying to configure some of the carrier aggregation cells, and somehow there is some failures in that. So this increasing the probability that you'll having RSC establishment, which might lead into drop as well. And the third part, in case if you have, as shown here, uplink carrier aggregation being enabled, not only downlink. So in case of uplink carrier aggregation, this is actually will cause a power limitation, because usually the user need to use for each carrier, it needs to transmit the different power. For example, as I will be highlighting in the next slide, for example, if you have a 23 dB maximum power, so the power need to transmit it between to be split between the two carriers, so the power will reduce by 3 dB. It will be around 20 dB. And assume also you have 3 carriers, it will be go even to 17 dB. So the uplink carrier aggregation in general will limit the uplink coverage, uplink transmitted coverage for the users. So this also can be reflected in the coverage. That's why usually it's being recommended to disable the carrier aggregation during using the VoLTE codes. Let's try to get a figure about this particular area where we have uplink, how it will try to visualize how the power will be split, as mentioned here. So in general, this will be reflected mostly in the VoLTE code drop rate. Okay, as you can see in the figure on the right here, this is assuming that this is the transmission from the U side, and this is the UTX branches. You have two TX branches. The maximum power is 23 dB, and the main idea that you have one carrier for 4G and secondary carrier. So the user now to need to split the power of the 23. So he will send 20 here and 20 here. So this is actually will be reflecting into a less power for those particular users. Even though the max is 23, because the power is being splitted, he lost around 3 dB. And even though if you went for more 3 carriers, this is will reduce even more, and also for 4 carriers will be reduced for more as well. But this is mainly for uplink, and usually even if uplink you have it enabled in the network, usually the maximum supported by the users is 2, and I think usually it's rarely being used in general, but this is just from theoretical background. So this was showing an impact from the one of the networks. For example, you can see there is this simulation from one of the networks. As you can see, there is a good improvement of voltage drop rate after the carrier aggregation was being disabled. And you might not see this in different, like if you implemented in your network, you might see this. This depend on the network situation in general, user location, and many other aspects. For example, how many carrier aggregation you have in the network. But in general, it's being recommended to disable the carrier aggregation for VoLTE users. So let's move to the next feature. Actually, the next feature is, you can say it's exactly, or the next parameter is exactly the same concept as the carrier aggregation. It's for the NSA users. If you have 5G NSA or ANDC, it's also being recommended to disable that. Why? Because the first point again, which we just being highlighted, the power will be split between one leg being transmitted 4G and one leg for 5G NSA. So again, you will lost around 3 dB. So this is limiting your uplink coverage. And this is the main reason actually, because this is limiting your uplink coverage. So in this case, it's not recommended to enable the ANDC for the VoLTE users. So you not required to have this kind of splitting, or in general NDC being allowed for VoLTE users. You need required to go for this scenario. Also, other scenario that sometimes this kind of ENDC addition, it requires signaling, so there might some interference between the signal interference or race condition, or in other words, the procedures or process of the signaling of the call setup of the VoLTE also being conflicted with ENDC. So maybe in some vendors you will have this kind of conflict that will prioritize, for example, the ENDC addition over the VoLTE. So this might lead into, for example, a call setup issue for the VoLTE. But I think this issue is being usually the vendor address this issue through that prioritizing the VoLTE signaling over the ENDC. So the main limitation is about losing the doubling coverage. You will lose around 3 dB in case if you are using ENDC for VoLTE users. So it's also being recommended to disable the ENDC for the user in order to improve your drop rate. So this is exactly or similar to the carrier aggregation scenario, which being highlighted in the previous slide. Now let's jump to the last feature. Actually, the last feature, it's not particularly related to the VoLTE, but it's just like it can also be benefit for VoLTE. I have quoted these pictures from Share Tech Note. You can go there for Share Tech Note. I will add this video, the link in the video description. It's having even more details and very good details about the same particular thing. The main idea of the hopping in general, PUSCH hopping, this is can be having a very good improvement because doing something called frequency diversity. So let's just explain from the beginning. If you look into this figure without hopping, you can see this is, for example, the subband, which is the frequencies domain, and this is the time domain, the subframes and so on. You can see that all the resources being allocated, for example, at subband 0 or whatever resource block 0, whatever you can call it, it's being allocated here all over the frame. So there is no change throughout the frame allocation. The resources not being changed. And in case somehow if you have a frequency impairment, you have interference at this particular area, for example, at subband 0. So in this case, you would be interfered all the time. This where the frequency hopping can get some gain in case of the frequency allocation of frequency of the frequency hopping. For example, if you look into this picture, you will find that the first subframe, the resource being allocated here, and the second subframe, it's being allocated a different subband on different source block. So this is making like a frequency diversity, which accordingly can be reflected in your quality, and accordingly can be reflected in your coverage. So it can improve the packet loss and even the quality in general, the voice quality in general, which is the most. This is the main idea. And there is two types of the hopping, which is inter subframe, as you can see, which will be the frequency allocation will be each subframe, as you can see, change it each subframe. And there is intra subframe. For example, here the first part is being here, and the second slot, for example, is being allocated in the second slot is being allocated in different resource blocks. And again, the main idea that this is increasing the frequency diversity and can be reflected in packet loss. But this is actually cannot mitigate such issues because you are not expecting that you will have a clean band whenever you do a frequency hopping, right? Because this is not a frequency selective. Frequency selective, if you remember, we discussed about it before. It's selecting the location of the resource blocks based on the quality, correct? So this is like frequency hopping in general, like for sure the frequency selective, it will be more beneficial in terms of this particular scenario because it will selecting the clean resource blocks from the beginning. So this case actually can mitigate, but it cannot completely eliminate because again, you might have this kind of impairment of frequency in for example, in subband 3 whenever the allocation is being done. So the first feature we're going to start with today is semi-persistent scheduling. I believe you might be aware about this feature. It's a very simple one, which is again mainly used to reduce the BDCH congestion, like to have a BDCH capacity enhancement in general, and particularly to use in high load scenarios. So let's first try to recall what was the normal scheduling in the VoLTE. If you remember, the VoLTE packets is being transmitted every 20 milliseconds. So you will have the BDCH allocation or BDCH grant will be allocated every 20 milliseconds here. And accordingly, you will have your BRBs or resource blocks and the MCS, or the scheduling part, being allocated to the user every 20 milliseconds based on the BDCH allocation. So and BDCH grant allocation. So you can see, for example, in this particular scenario, we are assuming that this for particular users being moved, so they're having a different radio condition. So the InnoDB is scheduling different location of the resource blocks, for example, here, as you can see here, and also assuming you have a different MCS. So the resources being changed as you can see here.
While in the semi-persistent scheduling, what it will do, in order to save the BDCH, like to improve or reduce the BDCH condition, it will do the BDCH allocation only one time. In the beginning of the call, for example, it will allocate the BDCH, and this is BDCH will have background. It will have information about, again, the BDCH resources or BDCH resource blocks and MCS as well, moderation scheme. So, but in this case, it will be fixed allocation. For example, it will have a fixed number of resource blocks with fixed location and also fixed MTS. Let's assume, for example, MCS 15 or 14 or whatever. So the same resources and location for BRBs and MCS will be used all over the call. So this means that every 20 milliseconds, there will be no need to having allocation for BDCH resources. So this will save the BDCH and will have a great improvement in the BDCH allocation, as you can see here. But the main point here, which might result in some drawbacks, that the allocation or the scheduling information for the MCS and BRBs will be the same all over the call. And this is, for example, might cause a problems for example, if you're assuming in the high speed scenarios, whenever the user is moving with high speed and there is high variation in radio condition. So this might cause a problem, especially if the user moved, for example, from a good radio condition area to a poor radio condition. So this might increase the silent calls or even the drops or packet loss or whatever. For example, also in the scenarios where the user is moving from outdoor scenario to indoor scenario, so this can also cause a problem. So usually, like, this is a scenario-based feature. You can just enable in very particular scenarios whenever you have a very high congestion of BDCH, and also for the scenarios where you are not expecting a lot of variation in the radio condition. For example, let's assume you have one sites, IBS sites or indoor sites, where you know that the area is very well covered. So for example, you can enable the feature for this site. This is just an example. For sure, every network will have a different behavior, but I'm just giving you some ideas about it. And in general, there is some requisite for this feature. For sure, the user supposed to support VoLTE, plus there is the user support the feature itself, which is called semi-persistent scheduling. And in the next slide, I will explain how you can get the information whether the user is supporting the feature or not. And for sure that the ABC or the core network is supposed to support the IMS in general, IMS-based voice services. And here there is from the scheduling information, the normal scheduling here, that initially you will have a route setup PCI1, and then you will have the BCH allocation. For example, this is BH grant or order 1, and every 20 milliseconds there will be allocation for BDCH allocation. DCI information, for example, being sent with DCH order 1, order 2, order 3. While here for whenever the semi-resistive scheduling, initially there will be a wrap setup PCI1 and the SPS will be configured to this particular user. Then it will be activated through only one BDCH activation during the talk support or during the call in general. Once the call being released, the BDCH or the SPS will be deactivated through, again, sending a DCI from ENDC to the UE. So this is in general about the feature. Now let's move to the next part about how to check the capability of this feature. So as you can see here, for example, this is explaining how you can check the capability, SPS capability, whether the user supporting the semi-persistent schedule or not. For example, if you look into this figure, this is from the UE capability information message. Like whenever in 4G you have the UE capability information being sent. So you'll find under the UE capability message, you can just go UE capability information, then you'll find UE track capability, then under RF parameters, you'll find something called FGI or feature group indicators. And this is one of the very important messages to know about it, especially for the UE capability. As you can see, it's like consisting of 32 bits. Each bit of those is like indicating a particular feature, whether this feature is being supported or not. In the next slide, I will give some information about it, and I will attach the details about each of these bits, the explanation or definition in the video description. So for example, the bit number 29 here, this is showing whether the user is supporting the SPS semi-resistant scheduling feature or not. For example, if this bit is 1, this means it's supporting. If 0 means it does not support. So this is like simply what to do. The next part here, actually, it's about whenever the user, the IN will be configured the UE with SPS. This is the configuration of the activation. The configuration would be done through the layer 3, while the activation will be done through the DCI information. So for example, here, this is ROHC configuration message being sent at any time. it will have this SPS configuration downlink confirmation or even uplink. And if you'd like to get more details about this part, you can refer to this below link. It having very good information as well if you would like to go for more details about it. So yeah. So now let's move to the part related to the FGI feature to give more explanation about it. Okay, this is just like I quoted this table from 3GPP TS 36.331. This one you can see this is like showing the table for all the bits and under the FGI or feature group indicator, which each one of those bits like giving explanation or like addressing whether this bit supporting or related to which feature. For example, if you look into this bit 28, it's just showing to you TTI bundling. For example, if bit 28 is 1, this means a user supporting TTI bundling feature. If it's 0, this means it does not support. Same for 29 for semi-persistent scheduling, and same for the handover part. And again, I will attach the video description, the complete explanation for the 32 bits, because here I give some examples in the video description just for your reference in case if you need it for any other use. So now let's move to the next feature which we have today. The second feature actually is also one of the very good feature and also easy to understand features. For example, this is called downlink VoLTE bucket bundling. And from the name itself, it's kind of giving some explanation about this, how this feature works. For example, if you look into this, the normal scheduling again, which we explained the same in the previous slides, that the allocation will be every 20 milliseconds, and you will have your BDCH resource blocks and MCS and so on. And here you can see every 20 milliseconds you have BDCH allocation, and you have the related resource blocks for the BDCH and for the MCS as well. So you will have the packets here. While this feature, what it do, as you can see, it's called downlink voice packet bundling feature. And as explained here, this feature can bundle, or two voice packets can be bundled for the scheduling. What it mean by this? For example, you have one voice packet here and one voice packet here. So instead of sending two different intervals here, as you can see here, it will just bundle both packets together here. So we'll have more allocation for sure for the BDCH, but this will save the BDCH in the next interval. So the next interval you will not have any VoLTE packets because both of them being transmitted here, and this will be repeated again. So for example, the scheduling here, instead of 20 milliseconds, it will be each 40 milliseconds. So as you can see, this will save also a lot of BDCH, can improve the BDCH capacity, but at the same time also it's having a drawbacks or downside because it can increase the VoLTE latency. As you can see here, this is whenever we enable the feature before, we have seen an increase in the VoLTE latency. So this is one of the drawbacks. So again, this is also scenario based, depend on whatever the target or your target in the network where you need to optimize. So now let's move next to the last feature of today's video. Okay, the last feature here is called delay-based scheduling, and you can say this is kind of become a must feature where it must be enabled because this is have a very good impact in the voice quality and also in the particularly for the cell edge users, where it can improve the block error rate. Also, the voice quality will improve a lot for the cell edge. So how this feature work actually? Actually, this feature work based on the buffer delay, or you can say that the E2E will look into the users where it's having in its buffer. So if it's found some users where it's having a high waiting time, for example, the buffer delay for these users is very high based on some values. This might be depend on the vendors itself. So for example, assuming here UE1 having a waiting time more than 30 milliseconds, UE2 have 25 milliseconds. So this will be the priority of the scheduling. So the normal case scenario for the scheduling, you know that we have round robin, you have max over I, and you have this kind of things, if you remember for 4G in general. But in this case, we'll use this. This is how the feature will work. It will prioritize the users with high buffer or high waiting time, instead of the user was having less waiting time. So let's try to simulate this to see how this feature works. Assume this is your scenario. This is the buffer delay in the E2E side. This is the E2E side. And here we have UE1. UE1, we assume that the waiting time is more than 30 milliseconds. And you have CQI number 7. So assume here you have 3 packets for user 1, 3 packets for user 2, and 3 packets, for example, for user 4. And this user one is edge user. It's having a poor radio condition. It can be in downlink or uplink, but I'm just giving an estimation like that to just present that this user is kind of edge user. So if you can see this buffer delay, the arrow here indicates that the buffer delay is very high. So whenever the packet is up here, this means the packet has been waiting for a long time. So how the scheduling will be done for the users? In this case, the unit B itself will prioritize the packets with very high delay. So for example, the first packet will be transmitted will be this particular packet. So if you move this one, it will be the first packet to be transmitted to user one. Again, if you look into the second packet, still having a higher waiting time compared to the others. So if you click in here, also this will be scheduled for the users. Now moving for the second user having this packet, which is also having a higher buffer delay compared to the other users and the other packets. So this again will be scheduled. Here moving for UE4, which will be the same. So to be scheduled, then this one, then we'll have this one, then this one will be moving, and so on. This one, then we'll be ending for that one. So in this case, this is what it will do. It will improve the voice quality because you improve the waiting time, this user having a more faster scheduling, and for sure this will be reflecting from the KPIs point of view. You can see improvement, for example, in block error rate, especially in the uplink, and this is what we have seen before. And even from if you have the most drive, you can see also the voice quality will be improving a lot. So let me show you an example from one of the networks. For example, here after enabling the delay based scheduling, we have seen more than 20% an improvement in the uplink iPlayer, and also from the drag test at that time, we have seen improvement in the voice quality. And that's it. That's all for today's video. And this is the end of the end-to-end training campaign. I hope if you like the complete training sessions, I hope you can share it with your friends and colleagues. This is to spread the knowledge and also to get more reachability to the channel. And for sure, there is a lot of other things for the VoLTE which can be covered. But this is, I think, whatever we have covered in today's video is kind of very fair enough to get started with the video and even to reach into a very advanced level. So thank you very much and see you in the next video. And please press like and drop a comment and share the video with your friends. Thank you and see you in the next video. Bye bye.